Dr. Kiran,
Sir.
am I audible? Am I
Yes,
audible?
Sir. Yes, sir, you are audible. Yes, sir.
Okay, fine.
So far, all are looking, I mean, all videos are good and all audios are also good.
Okay, fine.
Yeah. Huh? Here, huh? Yeah. John sir is there, already there. Somebody has to record also. You are recording? I'm recording. Okay. Live also start. Yeah, in 4 minutes we'll start, please. Short tour.
वाला हो गया गाना गाना हाँ वो आ गया लेकिन एक ही लाइन हम लोग का लेकर दूसरे में खैर दिक्कत ये हमने दूसरी लाइन काट ये अभी बता देंगे आप वो हो गया गाना से आ गया है गाना संदेश को दिख रहा है
मैं आपको दे रही हूँ
बस इसको सेव कर दिया ये कॉलेज तो नहीं यहाँ पर टावर नहीं आ रहा है बाहर आए पर टावर दिखा है जी राकेश हाँ राकेश अरे ऐसे अरे
John sir.
Yes. Kiran, is everything okay?
Is everything fine? Yeah, it's fine. 2 o'clock we will start. Sir, our chairperson of the School of Applied Sciences, Professor John Tiruvadigal is here. So, Professor.
He has joined.
Okay.
Yeah,
Hello.
Welcome you all, sir. Welcome you all.
Oh, thank you.
Good to see you. Thank you.
Yeah.
He is the convener of ICON 2021.
Oh, very good. Thank you.
Sir, can we start the program, sir?
Yes, sir.
Thank you. Distinguished and esteemed guests, delegates, scientists, heads of the departments, deans and directors, principals of various colleges or schools across India, faculty members, colleagues, my dear bright young students and participants who are watching on YouTube Live. It is a glorious moment to extend my warm wishes to all of you on behalf of the organizing committee of the International Conference on Nanoscience and Nanotechnology 2021. We are indeed honored to have all of you here today with us for this program, Seeding Nanoscience in Young Minds, live interaction with nanoscientists, organized by the SRM ICON 2021 and co-organized by the Indian co-organized by the Indian Science Congress Association, ISCA Chennai chapter, in celebration of the Department of Science and Technology, DST, Government of India, Golden Jubilee Year. I am Dr. Kiran Mangalampalli, Research Assistant Professor, working at the Department of Physics and Nanotechnology, SRM Institute of Science and Technology. I would like to take a few minutes to introduce you about today's program. As part of the ICON 2021, we planned Seeding Nanoscience in Young Minds, live interaction with nanoscientists, an exclusive program for the bright young students of age group between 14 to 19 from India's top intermediate and tertiary colleges, aimed at creating awareness on nanoscience and nanotechnology and its applications in our daily lives. This is beneficial to the learners as we try and develop an interest in science at an young age, thus motivating them to take up science when they enroll at university. There is a growing concern that there are not enough scientists globally and locally to sustain us for the future. In our opinion, we need to start inspiring the next generation students at an early age and give them thorough grounding in science at schools and colleges. The novel properties that exist at the nanoscale and the applications that enable them can be used to inspire students of all ages. When I talk to a group of students and I tell them that gold can appear red at the nanoscale, or we talk about the allotropes of carbon, even young students can get the difference between the diamond and the graphite in their pencil. Or when I demonstrate water droplets dance on the superhydrophobic surface, the students' eyes just light up and they don't say just wow, but they ask how and why. Then we can dive into the science and technology that enable those applications. In my opinion, introducing nanoscience and nanotechnology at an early age is a great way to get budding scientists excited about STEM, science, technology, engineering, and mathematics. It's an interdisciplinary approach. And stay there where with new discoveries and applications announced daily. The opportunities are endless to use these applications to inspire the students. Also, we believe and hope that this program, Seeding Nanoscience in Young Minds, live interaction with nanoscientists, aligns with the Department of Science and Technology, Government of India's National Priority Initiative, Innovation in Science Pursuit for Inspired Research scheme for young students, to inspire and encourage them at an early age to choose science as career. For this program, we have sent invitations to principals of the NIRF Government of India ranked top 100 colleges or schools to nominate the best two students from each college or school. We received an overwhelming response from the participants of various educational institutions. We thank and appreciate them for their outstanding support in shaping this program extremely attractive and useful. Around 300 students across India from various colleges or schools have registered for this program. Our internal experts interacted with the nominated students on January 19th and selected 10 best students for awards for their excellent oration and knowledge on nanoscience and nanotechnology. The Indian Science Congress Association Chennai chapter sponsors the merit certificate and a cash prize of 1,000 rupees each to 10 students. The awards will be announced at the end of this interaction meeting. Also, providing the participation certificates to all the students who registered for this program. And we invite the interested students to visit our laboratories and do a small project on nano related thing during the coming summer. We are grateful to Professor Vijayalakshmi Saxena, an eminent scientist, well known for her research, teaching, and administrative contributions, and the General President of the Indian Science Congress Association for the year 2020 and 2021, for extending the fullest support in co-organizing the program, sponsoring the Young Student Awards, and agreeing to deliver the presidential address. We welcome you, ma'am. We wish to thank our world-renowned and esteemed scientists, Professor Chandapati Jagadish, the Australian National University, Professor Radha Boya, University of Manchester, and Professor Shinji Yamada, Kao Corporation, Japan, for accepting our request to interact with the bright young students and inspire them with their research findings. Our sincere thanks to Professor B.S. Murthy, Director, IIT Hyderabad, for kindly agreeing to deliver an inaugural address. Sir, we thank you very much from the on the behalf of the organizing committee. And our deepest thanks to Professor Kashmir Raja, convener, and Dr. Alagiri Sami, Secretary of ISCA Chennai chapter, for extending their fullest support. I thank all the students who showed an excellent enthusiasm in interacting with scientists and preparing well for today's program. I have an important person to convey my sincere thanks to. Without his incredible support, this idea wouldn't have come to on the stage. He is our beloved chairperson, School of Applied Sciences, SRMIST, Professor D. John Tiruvadigal. Thank you very much, sir, for giving us freedom to design this program. I thank our SRM management for giving encouragement and providing all facilities. Also, I thank my colleagues Dr. Ishwaraya, Dr. Abhay, Dr. Suresh, Vijay Kumar, Rudra Banerjee, Bhaskar, Venkat Ravindra, Anbu, Dr. Payal, and importantly, my PhD students, Ms. Saujanya, Jina Jaj, and Hajish Kumar for their hard work in making this program, prestigious program, successful. Now, with these few words, now I request Professor Kashmir Raja, the convener of the Indian Science Congress Association Chennai chapter, to deliver the welcome address. Thank you.
Good afternoon to everybody. With great pleasure, I extend a warm welcome to our esteemed guest, Professor Vijay Lakshmi Saxena, Professor Ashok Kumar Saxena, the past president, the one who gives the inaugural address, Professor B.S. Murthy, Director, IIT Hyderabad, Professor Chenupati Jagdish, AC, the Australian National University, Professor Radha Boya, the University of Manchester, Professor Shinji Yamada, Kao Corporation, Japan, Indian Science Congress Association officials, ISCA chapter conveners and executive members, deans, directors, HODs, faculty members of SRM IST, principals of various colleges, and the bright young students for this program. This program is being organized during International Conference on Nanoscience and Nanotechnology by the SRM IST and jointly organized by the Indian Science Congress Association Chennai chapter in celebration of the Golden Jubilee year of the Department of Science and Technology, Government of India, and the convener of this prestigious conference, ICON, Dr. John Tiruvadigal. The ICON is a biennial international conference incepted in 2010, organized by the Department of Physics and Nanotechnology, SRM Institute of Science and Technology, attracting researchers across the world working in the field of nanoscience and nanotechnology. The conference became a common platform for the path-breaking research ideas to motivate the young researchers in carrying out the state-of-art research work, leading to an interface between science, industry, and societal needs. SRM Institute of Science and Technology, in association with Shizuoka University, Japan, NCTU, Taiwan, GNS, New Zealand, ACCMS, Indian Physics Association, ICS India, Tata Institute of Fundamental Research, India, RMIT University of Australia, and Springer Nature is organizing this edition of ICON. More than 2,500 young students, scientists are participating in this conference. This year, the ICON organizing committee came up with an innovative idea of involving young students from the top NIRF ranked colleges in the age group of 14 to 19 in the international conference to inspire and motivate the next generation students towards science and technology by providing a venue to clarify their doubts in nano science and nanotechnology. In fact, it is an excellent opportunity given to the bright young college students to interact with the world-renowned nanoscientists. I am sure that many students will get motivated towards nanoscience and nanotechnology after the interaction, and they will be definitely elevated as future budding scientists. When the organizing committee informed us about the program, we, the Indian Science Congress Association, Chennai chapter, agreed to jointly organize and sponsor the event without any second thought, as the ISCA believes that it is vital to motivate next generation students towards research in science and technology for a better world. In this occasion, I thank and welcome our General President, Dr. Srimati Vijay Lakshmi Saxena, Indian Science Congress Association, Kolkata. And I also thank Professor Ashok Kumar Saxena, the past president of ISCA. We thank you, madam, for agreeing to be the president of this event and give the presidential address. I extend a warm welcome to Professor B.S. Murthy, an eminent scientist and director IIT Hyderabad for this event. And I thank him for agreeing to give the inaugural address despite of his busy schedule. Thank you very much, sir. I thank and welcome the world-renowned nanoscientists, Professor Chennupatti Jagadish, Professor Radha Boya, and Professor Jinji Yamada for agreeing to interact with the bright young students from various colleges. I extend my warm welcome to all the students, participants of this event. With this note, I wish to invite Professor Vijay Lakshmi Saxena to give the presidential address. Now, before that, I would like to introduce Dr. Mrs. Vijay Lakshmi Saxena. The great scientist, Dr. Srimati Vijay Lakshmi Saxena, has been elected as the General President of Indian Science Congress Association for the year 2020-21. With this honor, she becomes the fifth woman in ISCA's 108-year history to hold this prestigious position. Interestingly, her husband, Professor Ashok Kumar Saxena, also held this office in 2016. This makes the Saxenas the second couple to hold this office after A.K. Sharma and Archana Sharma. After her election, Honorable President of India, the Vice President of India, Sri M. Venkaiah Naidu, was quoted as saying that he was very happy with Saxena's appointment as the General President of ISCA, and that women need to be given equal and adequate opportunity to prove their merit. In an interview to a weekly news magazine after the announcement of this election as General President, Professor Vijayalakshmi Saxena said, despite progress, there are still very few women at top positions in the country in science and elsewhere. In the same interview, she added, it is not enough to keep women and science within a certain section. We need to do a lot more to uplift women, especially from rural areas, and their innovations. Professor Saxena had served as the head of zoology, DG College, Kanpur. He is, he is, she is at present the coordinator of Bioinformatics Infrastructure Facility Center of DBT, Government of India. She has more than 45 years of research experience. 32 research students have obtained a PhD under her able guidance. She has published 94 research articles, 20 books, and 72 abstracts. She is also the recipient of many awards and fellows. With this introduction, now I invite Professor Srimati Vijay Lakshmi Saxena to give the presidential address. Thank you.
Uh, Thank you so much, Professor Kashmir Raza, for your kind words for me. Very good afternoon to you all present here for this webinar. Respected Professor B.S. Murthy, Director IIT Hyderabad, Chief Guest of today's international webinar. Professor Chanupati Jagdish, Australian National University, Canberra, Australia. Professor Radha Boya, University of Manchester, UK. Dr. Shinji Yamada, Kao Cosmetics Company, Japan. Professor D. John Thiruvedigal, Chairperson, School of Applied Science College and Engineering and Technology, SRM. Professor Kashmir Raja, Convener, ISKA Chennai Chapter. Professor Algila Sami, Treasurer, ISKA Chennai Chapter. Dr. Kiran Maglampalli. All the participants of international webinar, guest speakers, faculty members, council members, chapter conveners, students, ladies and gentlemen, and media personnel. First of all, I feel privileged to have been granted the opportunity to express my views on such a relevant topic. I wish to thank Professor Kashmir Raza, convener ISKA Chennai chapter, for inviting me for this webinar to share my views with you all. I'd also like to congratulate all the young scientist awardees for getting the precious awards. Now coming to the nanoscience for young minds, seek to discover, describe, and manipulate unique properties of matter at the nanoscale in order to develop new capabilities with potential application across all fields of science, engineering, technology, medicine, better imaging and diagnostic equipment, energy efficient products such as fuel and solar cells, improvements in manufacturing for durable, lightweight, efficient production tools. It will provide an attractive job market for future scientists and technologists. So, today's webinar is of great help to choose career for young students on the very relevant topic, seeding nanoscience in young minds, live interaction with nanoscientists. I'm not going in detail because there are school children, they need to be motivated, and as well as there are many specialists here present which will give a specialized talk on this field. But I am giving just elementary insight about the nanoscience and nanotechnology. Nanoscience is the study of nanostructure and materials on an ultra small scale. A nanometer is 1/1000th of a meter of the physical and chemical properties of matter change at the nano level. Nanotechnology is a common word these days, but many of us don't realize the amazing impact it has on our daily lives. Nanotechnology has just emerged from fundamental research to the industrial application. The tremendous potential of nanotechnology is to improve the performance of conventional material and process is most promising. Nanotechnology refers to the field of modern research and is field of applied science which deals with the synthesis, strategy, and manipulation of particle structure ranging from approximately about 1 to 100 nanometers, which controls matter on atomic and molecular scale. So the main feature of it, the control of matter on a nanoscale. Scientists are discovering that atoms and molecules behave differently at the nanoscale. According to United States National Nanotechnology Initiative, nanotechnology is science, engineering, and technology conducted at the nanoscale. The application of nanoscience and nanotechnology has the potential to revolutionize a diverse range of fields from healthcare to manufacturing. It can be used across all the science fields such as chemistry, biology, physics, material science, medicine, engineering, agriculture, and electronics. In agriculture, nanotechnology is used to produce nanopesticides and nanoherbicides, etc. Whereas in medicine, it is used in drug delivery. Diagnosis of disease, nanomedicines are reported to have low side effects, high efficiency, and fast action. Nanoparticles may simplify cancer detection, etc. Nanotechnology is a rapidly expanding field. Scientists and engineers are having great success making materials at the nanoscale to take advantage of enhanced properties such as higher strength, lightweight, increased electrical conductivity, and chemical reactivity compared to their larger scale equivalents. Nanotechnology is helping to considerably improve, even revolutionize many technology and industry sectors: information technology, homeland security, transportation, energy, food safety, and environmental science, among many others. Major benefits of nanotechnology includes improved manufacturing methods, water purification system, energy system, physical enhancement, better food production methods, nutrition, and large-scale infrastructure, auto fabrication. Metals such as gases, liquid, and solid can exhibit unusual physical, chemical, and biological properties at the nanoscale, differing in important ways from the properties of bulk materials and single atoms or molecules. Some nanostructured materials are stronger or have different magnetic properties compared to other forms or size of the same material. Physicist Richard Feynman was the father of nanotechnology, and during 1981, Professor Norio Taniguchi coined the term nanotechnology. However, nanosite devices and objects have existed on Earth as long as life. The exceptional mechanical performance of biomaterials such as the bones or mollusk shell is due to the presence of nanocrystals of calcium compound. Another example is photography, which uses silver nanoparticles sensitive to light. Nanotubes are an ideal reinforced component of modern fibers. The most promising contemporary development includes the synthesis of new forms of carbon fibrine, C60, and carbon nanotubes. According to American Ceramic Society Bulletin, Volume 84, nanotube applications include nanoelectronic devices, transistors, tips for scanning, probes, microbes, biochemical sensors, catalyst support, gas storage, separation devices, drug delivery systems, self-healing technologies. Nanomaterials or quantum dot or nanoparticles can be represented as a cluster of tens to thousands of atoms, 1 to 100 nanometer in diameter. These particles also can be considered as nanocrystals. When the dimension of a material are decreased from macro size to nano size, significant changes in electronic conductivity, optical absorption, chemical reactivity, and mechanical properties occur. With decrease in size, more atoms are located on the surface of the particle. Nanopowders have a remarkable surface area. Nano-sized particles have been used to enhance the mechanical performance of plastic and rubbers. They make cutting tools harder and ceramic materials more ductile. More specific achievements of discovery of a highly ordered crystal nano structure, development of paints and finishing materials with self-cleansing properties, discoloration resistance, and high scratch and wear resistance, self-cleaning tiles, window glass, and mortars. Nano-engineered polymers are highly efficient superplasticizers for concrete and high-strength fibers with exceptional energy-absorbing capacity. Nanoparticles such as silica are effective additive to polymers and concrete with improved workability and strength. Nanotechnology has a great impact on our day-to-day lives on a daily basis. Faster, smaller, and more powerful computers that consume far less power with long-lasting batteries, circuits made them from carbon nanotubes could be vital in maintaining the growth of a computer power. Faster and more functional and more accurate medical diagnostic equipment. Lab on a chip technology enables point of care testing in real time, which speeds up delivery of medical care. Nanomaterial surface on implants improve wear and tear, wear and resist infection. On the medical front, nanosensors can also be used to accurately identify particular cells or substance in the body. Nanoparticles in pharmaceutical products improve the absorption within the body and make them easier to deliver, often through combination of medical devices. Nanoparticles can also be used to deliver chemotherapy drugs to specific cells such as cancer cells. improve vehicle fuel efficiency and corrosion resistance by building vehicle parts from nanocomposite material that are lighter, stronger, and more chemically resistant than the metal. Nanofibers remove nearly all airborne particles from the air before it reaches the combustion chamber, further improving gas mileage. Nanoparticles or nanofibers in fabrics can enhance stain resistance, water resistance, and flame resistance without a significant increase in weight, thickness, and stiffness of the fabric. Water filters that are only 15 to 20 nanometers wide can remove nano-sized particles, include virtually all viruses and bacteria. These cost-efficient, portable water treatment systems are ideal for improving the quality of drinking water in emerging countries. Carbon nanotubes have a variety of commercial uses, including making sports equipment stronger and lighter weight. For example, a tennis racket with carbon nanotubes blend less during impact and increases the force and accuracy of the delivery. Nanoparticles treated with tennis balls can keep bouncing twice as long as standard tennis balls. Most sunscreens today are made from nanoparticles that effectively absorb light, including the more dangerous ultraviolet rays. So they they also spread more easily over the screen. Nanoparticles are also used in food packaging to reduce ultraviolet exposure and prolong shelf life. Many drinking bottles are made from plastic containing nanoclays, which increase resistance to permeation by oxygen, carbon dioxide, and moisture. This helps retain carbonation and pressure and increases shelf life by several months. A huge variety of chemical sensors can be programmed to detect a particular chemical at amazingly low levels. For example, a single molecule out of billions. This capability is ideal for surveillance and security system at labs, industrial sites, and at airports. These are just a very few of the thousands of ways that nanotechnology impacts society. Important nanotechnology achievements seems to be announced almost daily. For example, researchers at George Washington University have discovered a way to draw carbon dioxide from the atmosphere and convert it into high-yield carbon nanofibers that can be used in manufacturing. Nanotechnology's greatest potential is for improving the state of the world through the purification of air and water. According to Marcus Antonetti, director of Max Planck Institute of Colloids and Interfaces at Max Planck Institute for Environmental Evolutionary Biology, he also said that the technology already exists to fix the atmosphere, but there is also a need to be focused on education and getting information to the public at large. Most people still don't know about these technologies. The best part is that all of this could happen immediately. If we simply spread the information in an understandable way, people don't read science journals. So they don't even know that all of this is possible. Nanotechnology has changed and will continue to change our vision, expectations, and abilities to control the materials world. These developments will definitely affect the world. I take privilege in humbly declaring that such academic gatherings through webinars should indispensably form an integral part of course curriculum in pursuit of students' career prospects. All the best wishes and a grand success for this international webinar. Thank you all.
Professor.
Yeah. Now I'll introduce Professor B.S. Murthy before his inaugural address. Professor B.S. Murthy is currently serving as the director of the Indian Institute of Technology, Hyderabad. Professor Murthy received a ME and PhD from IIC Bangalore. After serving at IIT Kharagpur for 12 years, he has been the professor at IIT Madras since 2004. His fields of interest are high entropy alloys, nanocrystalline materials and nanocomposites, bulk metallic glasses, grain refinement and modification of aluminum alloys, aluminum-based composites, in-situ composites, non-equilibrium processing, particulate technologies, thermodynamics, and kinetics of phase transformations. He has authored about 400 journal publications and 4 books. He has supervised more than 40 PhDs and 20 PhDs are ongoing. He has completed over 55 sponsored research projects and filed 20 patents. He has developed a wide variety of nanomaterials with exceptional structural and functional properties and demonstrated their technological viability. He is a recipient of more than 11 awards. I thank Professor B.S. Murthy for accepting to give the inaugural address. Now I invite him to deliver the inaugural address. Thank you.
Unfortunately, I was trying to speak a few minutes back to make this introduction a nano introduction, but I could not unmute myself, unfortunately. So we have, I think, 3 minutes time for my session before the next session starts. So I would like to be very, very brief, saying that nano is very, very exciting field. I have been enjoying for the last 3 decades or so. And I'm a microscopist mostly. When you try to look at these things in a microscope at extremely small scale, they are so exciting. At IIT Madras, I used to bring a lot of school children to show them how to see atoms in a materials. And it was so exciting when you see the brightness on their eyes when they see atoms at a small scale. We also have set up a facility called atom probe tomography at IIT Madras when I was there, where you can see atoms in 3D. And that's an amazing technology where you can look at materials, how atoms are arranged in material in 3 dimensions. And also this particular facility that we set up there can be remotely operated. So we have 8 partners in this national facility where people send us the samples, we put the sample in the microscope, and somebody from IIT Kanpur, Bombay, and so on operate it sitting from their location and try to see the exciting arrangement of atoms. So I welcome students who are all participating in this event today to come sometime to IIT Madras. Of course, right now, last 1 year I'm not there, but we can plan an event where I can be there and show you how exciting. Or come to IIT Hyderabad, where I'll be able to demonstrate how exciting nanoscience could be when you try to do things with your own hands. I used to have regularly a number of school students coming to my lab and doing internships in my lab, and working with such bright minds is always exciting. I'm sure all of you are waiting for a wonderful session, live session with people like Professor Jagdish and Radha and so on and so forth. And I'm eagerly looking forward to listening to some of them. And I wish this particular event a grand success. And I'm sure all the students will take along with them a twinkle in their eyes on this exciting field where so many people have contributed to this world in some way or the other. And the science has been growing, the technology has been growing. And I'm sure that some of these students who are listening to us today would one day be stars contributing in this particular field to a great extent. And more importantly, help the country in its vision for an Atmanirbhar Bharat to develop technologies in this particular field and help the country to grow to a great extent. There's so much that can be done, and we are all eagerly waiting for young minds to embrace this exciting field and contribute significantly as we go. Thank you very much for this opportunity.
Thank you very much, sir. Yeah, Professor Kashmiraja, sir.
Yes.
Yeah.
Sir, I thank Professor B.S. Murthy for his short and at the same time very, very interesting information. And he wished that the students should visit IIT Madras or IIT Hyderabad. So for this great gesture, I thank him, and I also thank him for giving this inaugural address. Thank you very much, sir.
Thank you very much, sir. So before starting the interaction, just for 5 minutes, I have invited we have invited Dr. Lillian Jasper. She is the principal of the Women's Christian College, one of the top NRF ranked colleges. Ma'am, we welcome you to this one, and we request you to share your opinion for 5 minutes time. Thank you. You can unmute, ma'am. Unmute. Yes, please.
I would like to congratulate Sir C.V. Raman Research Park of SRM Institute of Science and Technology for this program, Seeding Nanoscience in Young Minds, live interaction with nanoscientists. This is a rare and wonderful opportunity to ignite young students to think big. And I think when we were students, we never had such opportunities. Most often, great scientists would only be names in our books or, somebody whom we see on the screen at some documentary film or something like that. I think this is a great initiative. I'm grateful to you for including our students, and along with you, we hope that they will help build our beloved country to achieve efficient power sources and life-saving medical treatments. Today, we use nanoparticles of silver in our hand washes, especially with COVID around. All of us carry these things, and also bandages and other things, and zinc and titanium in sunscreens. And nanotechnology has entered our lives in a big way, like our chief guest, Dr. Vijay Lakshmi Saxena mentioned, without even sometimes us realizing about it. Events such as these will bring the importance of this field into the limelight and kindle the imagination of young minds. I think it is a great opportunity for students to also think about a career in this field, because not many people are aware of the potential that it has to offer. So again, thank you very much for this meaningful and interesting event. Thank you.
Thank you very much, ma'am. We thank you and appreciate your you have nominated students, and all the principals actually nominated students, and you made this program successful. So now now the live interaction begins to the students with the nanoscientists. I request Dr. Ishwar to introduce Jagadish very brief. I know he doesn't like introductions, but we have to introduce him just for the students.
Hello, everyone. First, before introducing, I would like to introduce myself. I'm Dr. Ishwar. I'm a research assistant professor in the physics department. Well, Jagdish sir, I hope you remember me when I emailed you from NTU regarding the DECRA. So, hello, sir. I also would like to say hi to Murthy sir, because we always used to access his LTM laboratory. And Radha Boya, because of her extremely exponential growth, so I could hear a lot of her latest activities. Well, I'm very privileged to introduce Professor Jagadish, because whenever I read the Professor Jagadish biography, it's I would like to be a student rather than a faculty. It's lots of learning activity that one can get just after reading the biography. So I might need more than 30 minutes to read out all the achievements what Professor Jagadish achieved in the last 30 years, and not just credentials, but also some sort of it's the endowment programs to help students from developing countries So it's I think it's a personal pocket money that Professor Jagadish and wife launched a program that's the Chennupati and Vidya Jagadish Endowment Fund, where I see the news. Lots of students are already getting benefit and they're visiting Australian National University. And in fact, it's a more than science that is crediting to the society, and the people are fortunate enough to get the opportunity. So as I said, it's a short bio. So Professor Chennupati Jagadish, as when I Google it, is born in Vallurpuram, that's 8 kilometers away from Vijayawada. Sir, I'm from Kannur district, that's 8 kilometers, 70 kilometers, Nandyal district, Nandyal Taluka. And I'm also, that's a Prakasham district also, I'm aware. So, so Professor Jagadish is a companion of the Order of Australia. That's the highest civilian honor awarded by the government of Australia. And his PhD MPhil is from University of Delhi, MSc Tech from Andhra University, and BSc from Nagarjuna University, and worked in SV College, Delhi University. And after that, Professor Jagadish moved to Canada, Queen's University, before moving to the Australian National University in 1990, where he has established a program, research program, especially after attending Professor Jagadish talk on nanowires. One can do wonders in nanowires. So, I mean, I heard this is the third time I'm hearing Professor Jagadish talk. It's every time it's a new piece of information that you can always revise your fundamentals, where it starts from the fundamentals to devices and the applications. So that's a excellent research seminar that we heard from Professor Jagadish. So I would like to read out some of the awards that Professor Jagadish.
Dr. Ishwarya, Doctor, please stop
Yes.
that. Let me interact with students. They
Yes.
ask them to Google my name and they will find all the information.
Yes, sir. Yes,
Please.
sir. Yes, sir. Yes, sir. I would. Yes, sir. With such a very short bio, so I would like to conclude.
Now, Professor Jagadish, I request you to share your 5 attractive slides for the students.
See, I can find that
Yeah.
one. Okay, just give me one
Before
second.
interaction, actually, we planned that some 5 slides, if they can see,
Sure.
then they will come to know what kind of
So
research
let me
they're doing.
see, and so I'm trying to open this one, and let me see whether it works. Share. Okay.
Yep.
Okay. Good.
Yeah, we're able to see it.
Okay. Good. Okay. Thank you very much. And first of all, I would like to thank the leaders of all the leaders of the SRM University, and also all the leaders of ISCA, and also the distinguished guests and others for inviting me to participate in this important interaction with the future leaders of science and technology. I call them. I don't call them as students, and I consider them as the future leaders of science and technology. So it's been mentioned that I work in the field of semiconductor nanowires, and so basically, let me go to the really straight to the point. And all of us learned about the mechanization, first industrial revolution with the steam power, or second industrial revolution with electrical power, third industrial revolution with the computer power and automation. But in the fourth industrial revolution, people are predicting that we'll be merging the digital world and then the biological world together. So that means the human-machine interaction will be the major aspect which is going to play an important role. And the light is one of the major sources of information which we really get. And about 80 to 90% of the information we receive and in our brain is through light. So that means we really need to develop the new optical technologies which are based on the nanotechnologies in order to be able to really create this fourth industrial revolution, and where light-based technologies are going to play an important role. World Economic Forum has identified that in 2018, some of the technologies which are needed in the future are holographic displays, where in the future, you'll hopefully be able to see people in the hologram images from the phone itself, rather than having to go to a big laboratory where you have to create the holograms or so. Wearable optical sensors where you'll be able to monitor your health continuously, and also light navigation and communications like autonomous vehicles and then vehicle-to-vehicle communications or so, and 3D vision and gesture recognition, and enhanced machine vision and augmented reality. All of them are going to play a very important role in terms of the future technologies, in terms of the fourth industrial revolution. And optoelectronics, and that's the area which we work in, and optoelectronics is nothing but conversion of electricity into light by using LEDs and lasers, and conversion of light into electricity using solar cells, for example. So really, developments in the nitride-based semiconductors has led to the large area displays and LED lights. Blue LEDs were a missing link, and then these Japanese scientists have developed this blue LED, which has allowed us to be able to really make these white LEDs, and then that really revolutionized in terms of energy consumption issues and LED lights globally. That made a huge impact globally. Again, we work on LEDs and we work on lasers, and then we work on photo detectors, and we also work on solar cells. And then mainly we are focusing on something called nanowires. So nanowires is nothing but a semiconductor material, or it could be a metal as well. It's 10 to 10 tenths of nanometers in diameter and then about a few microns in length. Okay, like a wire, but it's a nanoscale dimensions. And these nanowires have got lots of applications, particularly both in electronics and photonics. And then in fact, we are making a wide variety of nanowires. These are matchstick-like nanowires, these sort of a branch nanowires, nanotrees, nanomembranes. And then really exciting development, as Professor B.S. Murthy has said, it is like a kid in the lolly shop. You know, this nanotechnology is providing and allows us to be able to really play with the atoms and then be able to really make whatever the structures you want to have, and thereby you'll be able to get new properties and also new functionality in terms of making devices. We work on a wide variety of devices, lasers, LEDs, terahertz detectors, solar cells, using nanowires for splitting of water to generate hydrogen. And also most recently, we've been using nanowires for really engineering the neurons so that our ultimate aim is to be able to create a brain on a chip technology so that you can help people with the dementia and then all sorts of difficult mental problems, particularly with the aging population. Dementia and Alzheimer's disease and other things are a major issue. And then those are the futuristic technologies which we are really trying to develop. I will not spend huge amounts of time in going into the details of these ones. It is an example of the case where we're able to demonstrate some lasers, and these are some of the smallest lasers. And I can put about 20 to 30 lasers within the width of your hair. That really tells you how tiny these lasers are. And we're also making flexible LEDs. Flexible LEDs are very useful for using for flexible phones or the foldable phones, foldable computers. And so that means flexible LEDs are also going to play an important role. Again, we're using nanowires for that application. And we've been also using them for terahertz detection. Terahertz radiation is used for security applications and biomedical imaging applications, wireless communications also. Again, jointly with Oxford University, we're developing a very, very tiny terahertz detectors, which allows you to be able to create high resolution biomedical imaging or so. Again, we're working on nanowire solar cells. Again, we want to work on flexible nanowire solar cells. So that means in the future, you'll be able to have a solar cell which is on your backpack. You'll be able to start charging all your smartphones and other electronic devices, and again, provides the flexibility. Again, we're using nanowires for splitting of water to generate hydrogen, which is a clean energy source. And finally, in fact, there's a work of Dr. Vinay Gautam, who is now a lecturer at Melbourne University. In fact, Professor Radha Boya and Dr. Vinay Gautam did their PhDs at a similar time at Jawaharlal Nehru Center. And then she's really developing innovative technologies in terms of being able to use these nanowires and engineering the neurons in order to be able to really get them, really help people with dementia and other brain damage and other technologies also. I think I'll stop here. And it is important for me to really interact with people rather than me spending a lot of time talking about the details of our work. I'm happy to answer any questions you may have.
Thank you, Professor Jagdish. Yeah, they have a lot of questions. I received more than 300 questions. I may not be able to ask all them, but we will do. Before that, I asked actually Radha Boya also to show few attractive slides to the students. Before that, I asked that I request my colleague Dr. Ambu to introduce Radha short bio.
Thank you, Dr. Kiran, for giving me this opportunity to introduce a young scientist, Radha Boya. Radha Boya is a professor and Royal Society University Research Chair and Kathleen O'Leary-Shah Fellow in Department of Physics and Astronomy at the University of Manchester. She obtained her PhD in 2012 from JNCASR, Bangalore, India. Then she moved to Northwestern University with Professor Chand American for the first postdoc. After earning Marie Curie Fellowship, she joined University of Manchester with a technology review innovator under 35, L'Oreal UNESCO International Rising Talent 2018, and Odyssey Morlow Award, etc. She is currently working on fundamentals and applications of atomic scale nanocapillaries. She has published several papers in Nature, Science, Nanoletters, etc. With these words, I would like to welcome Professor Radha Boya. And on behalf of ICON 2021, I thank her for accepting to conduct this program live interaction with the young scientists. Thank you. And welcome, Radha Boya.
Thank you, Ambu. Yeah.
Thank you. Thank you for the kind introduction, Ambu. And my pleasure to be able to speak to you all today. And thanks so much for the kind invite. So as already introduced by Professor Jagadish, so we have new technologies. So it's new revolutions. Once upon a time, it was all about industrial revolution. And then we had plastics, which also revolutionized the way we interact with many technologies. So these technologies are often enabled by new materials. So today I'll just talk about one such material with you all. So as we all start our education, first thing we always when one starts their writing their words is with pencil. So I'm sure you all have written words with pencils on papers. So I would like to say there is a nanoscience in pencil. Have you ever wondered what you leave on the paper when you write with pencil? So the tip is dark in color, right? And that's made of graphite powder. So it's a graphite powder mixed with a binder called clay. So this the darkness of we have all heard, HB, 2HB, 3HB kind of pencils. The darkness varies, depends on the composition of this mixture. So this is a nanocomposite, which is a very primitive nanocomposite and very powerful example to illustrate the nanoscience is ever present. So this graphite is a naturally occurring crystal. It's a layered material. It is layers of carbon sheets. So this is well known, and it occurs in the Earth's crust. So this graphite was well known. So what is new here is the isolation of one layer of graphene from the graphite. So I'll tell you a true story. This is slightly difficult to believe that a combination of such a graphite layered crystal with Scotch tape led to Nobel Prize. So, but it is true. This is a true story. So what happened is how it happened is like this. So in Manchester, the place where I'm currently working, in the group where I'm currently working, 10 years ago, two scientists were awarded a Nobel Prize for their discovery and isolation of graphene. So all they did was to take such graphite crystal and peel off layers with Scotch tape. So that's all they did. And later on, lots of discoveries followed. So followed them. So lots of a new field was created. Lots of researchers across the globe started working on graphene and discovering new properties of graphene. What is so exciting about graphene? So why everybody jumped into graphene? It became a superstar of research area where everywhere in the world you see somebody or the other working on graphene. So what was so exciting about it was the first time it was proved. It paved a way to a new class of materials, which are two-dimensional. So we see everything around us is three-dimensional, right? So in materials as well, three-dimensional.
Dr. Radha?
Yeah. I think I lost for now. Am I back?
Yes, you are back.
Yeah, I'm so sorry. Yeah. So sorry about that. It's quite unstable. So first time it was proved that a two-dimensional material is stable. Until that time, it was believed that two-dimensional materials are not stable and they would roll up to make three-dimensional materials. So this was the first time a two-dimensional material was proved to be stable. And following which, it was it was quite a realization of new types of materials. So graphene is highly transparent. It only transmits 2% of light, less than 2% of light. So this is an image of graphene. So you can barely recognize the difference between air and graphene in this image. And it's light, highly conductive, and it's stronger. So the superlatives, the list of superlatives continues. So we can make use of lots of applications of these, lots of properties of graphene to realize them into applications. So it's lighter, it's lightweight property, and its stronger nature can be imparted to materials in combination with it. So this is one example where this car has components made up of graphene composites. So it can be formulated into inks and print on textiles, on fabrics. So you can have sensors integrated into your simple clothes, or it could enhance the sportswear. So these are just few examples, and it is impermeable. So it is highly impermeable. It is, even though it is 1 atom thin sheet. So 1 atom thin is 10,000 times smaller than a human hair. It is so thin, yet it is highly impermeable. It is equivalent to a kilometer thick glass in terms of its permeability. So it is highly impermeable to even the smallest of gases. So far we spoke about one material. So it's not just graphene, which is so exciting. It's a key to a new class of materials which are two-dimensional, which are 1 atom thin. So there have been lots of discoveries of new materials, and importantly, we can now combine and mix and match these materials to make heterostructures out of them. So you can envision and create new types of materials which do not exist. So these are artificial sandwiches which do not exist per se in nature. So this is one such heterostructure where you can see. So far, I told you they are layered materials, right? What is the proof? So all the things I showed you was schematics and images. So this is a microscopy image of one such sandwich, which has different layered materials, and each bright line that you see running across here is one atomic layer. So thanks to such powerful microscopic techniques, we can see these materials. Clearly. So we can clearly see the different thickness of these materials, because suppose moly sulfide has a metal atom, so it's quite thicker than graphene, which has carbon atoms. So not only that, we can combine the materials, we can design the angle at which they are combined. So for instance, this angle of combination of these two layers of graphene. Graphene is a highly conductive material, but it's not a superconductor. By just combining two layers of graphene at a certain angle, so this is the very funny thing. So it's known as magic angle, because no one knows why this angle works. So that's why they just named it as magic angle. So by just combining two layers of graphene, so we can achieve superconductivity, which is completely against any conventional known theories of superconductivity. So it is quite exciting, and it's not just academic research. So we have a complete building dedicated to this research. So National Graphene Institute in Manchester, United Kingdom. So these are our labs. So where we work on fundamental concepts. So unveiling new properties of two-dimensional materials. And it's not just academic interest. So there have been lots of companies with vested interest in exploiting the properties of graphene and two-dimensional materials. These are only few examples, and I'll conclude with few examples where the opportunity of graphene has been realized. So smartphones, so it's transparent and highly conductive. So, and it's also highly thermally conductive. So smartphone technology has already started using graphene materials for cooling better. And trainer shoes and sportswear. So these are because of the nature of graphene, which can mix with other materials like rubber and impart its own properties to the composites. So it can be used in trainer shoes, sportswear, and even rubber tires, which last enhancing their lifetime. So even into construction industry, it has made its way into construction industry. So graphene enhanced concrete. So because of the extreme strength, and also it enables use of less materials, less water. So it can reduce the emission of greenhouse gases. So what do I work on in this? So this is a huge area, so where everyone is working on. So what do I work on? So I'll conclude with that. So I'm working on a very small area, which is using graphene. So I've told you that we can take Scotch tape and isolate one layer of graphene. So what if we isolate one layer of graphene, but not from the top of the crystal, but from the middle of the crystal? So we remove one layer of graphene from the middle of the crystal. What do you get? So you get a tunnel which runs across the crystal. So this tunnel is 1 atom thin, and this tunnel height can be tuned by the number of layers that you remove. So this is what I'm working on. So this is a 2-dimensional empty space. So it's just opposite of graphene. It's not the graphene itself that I'm working on. So instead of discarding the graphite, you focus on the graphite. And this is where my work and my research theme is on. So and I fill these tunnels with various materials and study their properties, how these materials behave under such extreme confinement. So with that, I'd like to conclude, and I'm very interested in interacting with you all, and happy to take any questions. Thank you.
Thank you, Radha. That's an excellent presentation. I hope all our students, already got excited and motivated. Now we have another scientist, Professor Shinji Yamada. I request my colleague, Dr. Rudra Banerjee, to introduce Shinji Yamada. Dr. Shinji will present his slides after the interaction, because I want you to keep excited, and that excitement I want to continue in you. So his talk will be after 4:05. So I request Dr. Rudra to introduce Dr. Shinji Yamada.
Thank you, Dr. Kiran, to give me the opportunity to present Dr. Shinji Yamada. It's a great pleasure to introduce Dr. Shinji Yamada to the young minds. Shinji Yamada was born in Sendai, Japan in 1965. He received his master's in engineering in metallurgical engineering at Tohoku University, Japan in 1991. Then he joined Research and Development Division of Kao Corporation, where he still works. Kao Corporation is a world leader in chemical and cosmetic industry. During this period, he worked as a visiting researcher in Jacob Israel Chilvis Group at the University of California, Santa Barbara in 1995-96, where he learned the surface forces and nanotribology measurement. He received his PhD in applied chemistry at Tohoku University in 2004. From 2013 to 2015, he worked as an associate professor at Tohoku University to participate in the National Research Project of ultranofriction. In 2015 to 2017, he was a visiting associate professor at Tohoku University. He is now a senior principal research scientist of Kao Corporation and also a visiting professor at Nanotribology Research Center of the University of Electrocommunications, Tokyo, Japan. His main research interests are thin film rheology and tribology, surface force measurements, physical chemistry of surface and thin films, and skin cleansing and hair shampoo formulations and their characteristics. He published more than 50 scientific papers and book chapters and delivered more than 50 invited talks. So with this brief introduction to Professor Shindi, I would like to introduce Professor Shindi, and Professor Shindi, you will be going to have a great time, because last time when we interacted with these young students, they all were very interested in how the nanotechnology works in anti-aging cream and sunscreen and other things, which is you are a world leader in this thing. So welcome to SRM Institute. Now the session is over to the students.
Yeah.
Thank you.
Thank you, Dr. Rudra. Yeah, thank you. So Dr. Jagadish, Dr. Boya, and Dr. Rudra, Dr. Shinji Yamada. So the first question comes from Ayushi Das. Ayushi? Hello, Ayushi Das?
Well,
yeah.
I'm Shinji. Shall I start my talk?
Your talk will be at 4 o'clock. Yeah, after 1 hour interaction, you can present the talk. Yeah.
Okay.
Now I invite Ayushi Das. You please unmute. Yeah, Ayushi Das.
Hello.
Yeah. Yes.
Am I
You
audible?
please interact with the scientist. You can.
It was lovely to listening to all of you. Your talks were really motivating, and nanotechnology is such a promising field. So I am basically not from the physics background, so my understanding of the subject is a little weak. So while I was reading all the research advances that have been made in this field, I wanted to understand, like, when we go down to the nanoscale from macroscopic objects, what exactly causes the properties of the material to change. Like one of you have already said, gold is not golden in color at the nanoscale. Why is that? Like, what causes those properties to change at the nanoscale?
So Jagdish.
Okay, so maybe I'll take this one, and then that Ayushi, thank you very much for an important question. First and foremost, you don't have to be a physicist to work in nanotechnology. So in nanoscience and technology is such a multidisciplinary field, and then people from physics and chemistry, biology, engineering, and all sorts of people are working in this area. So please don't think that you need to be a physicist. So what happens when you take a material, it go to the
Niveda.
So the number of atoms on the surface become quite significant numbers with respect to the number of atoms in the volume of the material, for example. So that means the surface atoms have got a broken bonds. They all want to interact with the surrounding medium. So that means they could be used for sensors and catalysis and a range of applications you can make use of. The second thing, what happens when you go to the nanoscale is the quantum properties of matter comes into picture. If you take a material like a semiconductor like cadmium selenide, in the bulk form, it looks very grayish color. But if you really make into nanoscale of different dimensions, and then they all emit different colors of light, if you shine a UV light, for example. I cannot explain using classical physics how a material which really emits different colors of light. But if I do the quantum mechanical calculations, and it becomes very clear, the electrons in the system have got a different energy than in the bulk material. So that's why you end up having different colors of light coming out of it. In terms of why this gold is different colors of different things, this has got something called a plasmonic properties. Suppose if you shine light on gold, for example, and then light is nothing but a wave, for example. So this wave, electric field of this wave, the electrons in the gold nanoparticles are also really moving along with this electric field of the light wave. So in the process, they end up having different colors of light depending on the dimensions of the nanoparticle of gold which you're using. Okay, essentially it's a plasmonic property.
Okay, thank you. And I also have a question for Radha Boya, ma'am. I was reading about your research, and it's like coming up that graphene nanoparticles are also used for water purification. So the tunnel which you are working on, how does that help in water purification?
That's an excellent question, Ayushi. So the tunnels that I'm working on, they are of almost the dimension of water. So the water size, one molecule size of one molecule of water, the size is about 2.8 angstroms. This is the size of hydrogen with 2 oxygen atoms, right? So this is the size which we can, very close to this size. The size of one tunnel, the height of one tunnel is about 3.4 angstroms. So we are reaching the size of the molecules. And the size of the salts, like you have salts which are like sodium chloride, table salt, right? So these are also ions. Right? Sodium is an ion, chloride is an ion. Sodium is again surrounded by water molecules, and chloride is surrounded by water molecules. When you dissolve salt in water, is what happens. You just separate ions, and there are water molecules around it. So the size of this one sodium ion, along with molecule, is much larger than the water size. So it's about 6 angstroms. So we can tune the membranes. So usually in water filtration, there are membranes used. So the membranes have pores, right? So what I'm working on is on the fundamental side. So by tuning the pore size, by tuning the pore size very close to this size of the molecules of filtration, so we can achieve size-specific sieving. So it's like filtering the molecules by size.
So we can also select the particles we want to remove.
Yeah, so by the size.
Yeah, by the size. Okay.
Yeah, so I'm also working on gas molecules and like pollutants. So they all of these molecules have size. So we
So
can
that even acid water can be purified, like acid rain which we get, we can also reuse the acid water for some other
that's a
purpose.
good question. So acid is a slightly different scenario. I think acid, so when you have protons, so when you have protons in the water, protons are very easy to permeate through water because they make and break the hydrogen bonds. So these are H plus which can make and break the hydrogen bonds. But that's an excellent question.
Thank you so much, ma'am. It was lovely interacting with you. Thank you so much, sir.
Same here. Same
Thank you,
here.
Aishi. Thank you.
Thank you. Bye-bye.
All the best, Aishi.
Next, we have Ritvika Panda. She is a 12th class student, and she is from Dev Public School, Chandrasekharapur. Aishi Das was actually from Mirinda House, New Delhi. So, Ritvika Panda, you please unmute yourself and then you speak. You ask the question to scientist. Ritvika Panda, you please unmute.
Am I audible?
Yeah, you're audible. Yeah, go ahead.
Yeah. I read about, when I was reading about targeted drug delivery using nanobots, it was written that the nanobots interact with only those cells which are, suppose in cancer, the nanobots interact only with those cells which is cancerous, and they send the drug only in that location. So how do they interact? I read about interaction with covalent bonds, but I do not get how actually they interact with the bonds.
Radha, you want to take the question or you want me to take it?
Jagdish, I think it's you. You can take it. So you're also working with drug delivery, isn't it? So yeah.
No, that's right. So basically, in the case of drug delivery, there are many drug carriers we make use of. For example, it could be a nano cage of carbon, or otherwise a polymer, means a capsule which you really encapsulate this drug into, and then you functionalize this one with some particular structures, and then they are only allowed to be able. They have the ability to only be able to interact with the cancer cells, not the healthy cells, for example. But also, most interestingly, the cancer cells are also more porous. So that means, it's much easier to really be able to try put these sorts of capsules into these porous structures than the healthy cells, which are not as porous. So in the process, you can activate these, for example, if you by essentially these capsules can be activated by, for example, this polymer is so chosen such that in the medium there, it starts dissolving on its own and starts releasing the drug, for example. You can also make these capsules of polymers, for example, make it more porous so that drug is gradually coming out. So thereby, rather than sending it suddenly to the body, then that becomes like a shock, for example, sort of thing. The treatment could be very, very slow. One of the advantages, as you know, is that you're not really interacting with the rest of the body. So that means the side effects are much less. And also that you'll also be able to use a very small amount of drug. That means you can also reduce the cost of the treatments as well. So both ways, it's very advantageous. So that's why people are really developing this targeted drug delivery. It's a long process because, as you know, that whenever you're dealing with these things with human beings, we need to make sure that there are no detrimental effects while they're helping the people to really recover from something. For example, if I'm saying in a particular molecule, the capsule, what is happening to that one after the treatment is over? Is it sometimes people attach these things into the nanoparticles, for example, where these nanoparticles end up being, you don't want them to go and sit in the kidneys or liver or something, then it get more problems as well. So these are the things which community is looking at and exploring to make sure, and it's only doing the job which you want it to do, but it's not creating any unwanted impacts on the body of the people. So that's the thing. That's why these sorts of technologies will take a long time before they could be really used in the real world. It's a very good, very good question, Ritvika.
It's very interesting. I had another question. When we talk about nanoelectronics, when we go to the transistor level, how they are getting smaller and smaller by the time. So once the transistors become very small, because we're dealing with electrons, quantum mechanics also come into play. So we know that nanoscience and quantum mechanics, they are two very different branches. So how do you relate these two?
Okay, that's a very good.
If I may,
Go ahead, Radha. Please, Radha, please go ahead.
Thank you, Professor Jagdish. If I may take this question, that's a very interesting question, and basically it forms the heart of the nanoscience. So these are not, I mean, I'd like to say these are not two branches which are very different. So you can actually see the effects of quantum very much at the nanoscale. So you will see in nanomaterials, the electronic levels can become discrete. So they become quantized. So you will see new quantum effects. So the electronic levels of nanomaterials are no longer the same as bulk.
He made you co-host.
So you will see the effects of quantum in nanoscale. So especially as we go down further and further, less than 1 nanometer, these effects are prominent. So I would say, do not consider them as separate branches. You will see very much the effects of quantum in all branches of quantum in nanoscience.
because
So Professor Jagdish, you may add to it if you have.
Yeah, sure. Thank you, Radha. I think, of course, Professor Radha Boya has already gave you the information. So as you know that already the 5 nanometer electronic chips have been released by Apple, manufactured by TSMC in Taiwan. Already Samsung and TSMC has demonstrated transistors which are as small as 2 nanometers. So then, of course, when the circuit designers need to really keep this into effect, take into consideration when they're designing these devices, and how the transport properties of the electrons are changing in these nanostructures, and then they have to design them carefully in order to be able to take that into account. Thereby, that computer chip design itself becomes much more different than the old designs which people used to use, and that's where the complexity comes. And then also some of these materials, for example, if you put some dielectric layer to really confine the carriers, and then some of the carriers may tunnel through. So that means how to really avoid the leakage of the current and all these things when people have to look at sort of thing. So those are the challenges people are exploring at this stage. Yeah. Very good question again, Ritika.
It's fascinating. It was an honor talking with you. Yeah, it was an honor talking with you.
Thank you, Ritvika. Hope you are happy.
Yeah,
So
of
next
course.
is a 9th class student Kalanidhi Maran. Actually, he did very well in during our interaction. I hope he will ask now a very good question now. Kalanidhi Maran,
Yes,
can
sir.
you unmute yourself? Yeah, go ahead.
Good afternoon, sir and ma'am.
Your video? Oh, yeah, okay.
Yeah, good.
So I have a doubt. My doubt is that there are some nano filters, right, which filters all the bacteria and all the minerals. So my doubt is that human body needs some minerals and good bacteria and microbes in the water and other liquids. So won't it get filter and won't we get side effects by consuming the water?
Indeed. So if I may take this question. So that's a very good question, Kalanidhi Maran. And it's, in fact, firstly, I should say, like, it's very nice to know that you are interested in science at a very, young age. So it is indeed true that we need good bacteria. We need lots of minerals to be able to have good health. So most of these filtration mechanisms, most of them are based on particular principle. So the one that I mentioned to Ayushi, for instance, is based on size separation. So you simply filter out everything beyond that size, right? So it's like physical sieving, you just take a sieve and you just filter out everything beyond that size. There are also filtration principles which rely on chemical interactions. So you have a certain chemical interaction, then you can filter only those particular molecules. So it is indeed, so usually when desalination plants, wherein you take seawater and filter all the salts to get the pure water. So you will filter out everything. So you filter out all the minerals as well. So later on, the minerals are added so that you get the good, good amount of minerals for your health. So this is in fact a problem. So which currently I think it's not very easy to choose between good minerals and salt because of the close match between their sizes and also reactivity and diffusion. So these are the common principles which are used. So in fact, technology has to improve and develop to adapt these. So usually post-processing is done. Obviously, maybe it's the only way currently, but in future it will change for sure.
Thank
so
you.
Professor Jagdish, you may have anything to add. You can.
No, I think Radha, I think you've really answered it very well, and it's a matter of really choosing what you would like to have, which you don't want to have. First and foremost, you clean up everything, what will happen is that you're getting rid of unwanted bacteria. So then afterwards, you can add whatever the minerals which you would like to have in the water. And also you can take things like probiotics and other things to be able to get a good, healthy bacteria in your gut, rather than having nasty bacteria being there and creating a lot of problems for you. It's a matter of choosing the right ones which are useful for you and getting rid of the unwanted ones, or adding those ones later. Sort of. Okay. If you don't purify completely, then the size selection becomes very, very challenging, because good bacteria and bad bacteria have got similar sizes. How do you really be able to differentiate one to the other? So,
thank you. Thank you, Kalanidhi Maran, for your interesting question. Next, we have Bhavashri Yalini. Bhavashri Yalini, are you available? Bhavashri, actually, she asked one question. I think this is for Professor Shinji Yamada. Can we replace microbeads in cosmetics by non-biodegradable nanoparticles?
Excuse me?
Yeah, one question. Can we replace microbeads in cosmetics by non-biodegradable nanoparticles?
Well, I'm not working in the field, so maybe someone else should answer that question.
Okay. Non-biodegradable nanoparticles. That is one question was related.
So again, can you repeat that one again, Kiran? Because since you're focusing on Professor Yamada, then I didn't much attention. Yeah, go ahead.
Can we replace microbeads in cosmetics by non-biodegradable nanoparticles?
Yes, people have been using in the cosmetics the nanoparticles of titanium oxide and zinc oxide and other materials. Again, it's a biocompatibility of these nanoparticles is an important thing which one need to really think about. When you change the size of the nanoparticles, what will happen is that, for example, if I take zinc oxide, it because of these quantum properties which Professor Radhaboya and I mentioned, it allows the visible light to pass through, but the ultraviolet light gets absorbed by these nanoparticles. So then what happens is that if you apply the sunscreen, you don't know you applied the sunscreen, or otherwise you can apply some makeup, and makeup already is protecting you from the UV radiation and things like that sort of thing. So then also people have done a lot of studies of what will happen to these nanoparticles, and so what is impact in the longer term. That's always one of the things which is a lot of debate is taking place. For example, people from NIOSH in the US, and they've identified that whenever you apply these sunscreens with nanoparticles, if you stay still, nothing happens. But if you start moving, then what happens is that these nanoparticles can start passing through your skin, for example. But if it's a biocompatible material, you don't have to worry about it. If it is not biocompatible material, you really have to worry about where they end up being, sort of thing. But another thing which we also need to think about is that suppose if you're applying a makeup, for example, you got these nanoparticles of zinc oxide or titanium oxide, you wash your face in the sink, and then this water is going to the water streams, and tomorrow fish and others are really taking these nanoparticles up, and tomorrow you may be eating fish. So that means you may be consuming nanoparticles as well. So that's why we are suggesting that you need to have the life cycle issues need to be addressed before using any of these nanoparticles particularly involving the human beings. So that's an important question which I've asked. And then I think there's more studies need to be done to make sure that you minimize the risk of using these nanoparticles in cosmetics and other things.
Thank you, Professor Jagadish. Next question comes from Chinmay Chahar. She is a second-year computer science student and Indraprastha College for Women, University of Delhi. Chinmay, you please unmute and go ahead. Yes.
Hello, everyone. Am I audible?
Yes.
Hello, everyone. I myself am a computer science student, and while reading about nanotechnology and its application in the IT field, a question popped in my mind that we are seeing nowadays the problem of electric waste is dooming our environment, both on land, in water, and even in space as space junk. So I would like to know more about, is it possible to make these electric chips, electric boards, and I mean such electric components as biodegradable using nanomaterials?
Okay, Radha, you want to take or you want me to take? Or?
So I can start first and maybe you can also answer.
Yeah, please go ahead. Yeah, sure.
So that's a That's a fantastic question. In fact, Kalanidhin Maran also texted me a question similar to this. I was typing the answer for him, so maybe I can answer both. So environment is a big concern for us now, and we have to protect all we can do, right? So biodegradability in all the day-to-day things that we use is an important factor. So, and especially electronic waste. So this is what is going to grow tremendously in more and more in future as well. So currently there are in an electronic chip, there are many components within the chip. There are metals, there are contacts of metals, there is an active channel in the transistor. So, and there is a plastic, which is a circuit board, So there are lots of materials. In each of these materials have to be taken care in terms of biodegradability. So at this moment, I think not all materials are degradable. This is where the electronic waste piles up. So same is true with batteries, right? So they have acids, and so this can contaminate the groundwater if not taken care, right? The soil, also the soil. So this is where so new materials. Suppose graphene. If you take graphene is carbon, all carbon, right? So maybe at this moment people are trying to replace one material or the other, not everything in the chip. So, but this is the way forward so most of the chips have multiple components, so which are carefully selected to optimize the performance. It's the customer in the mind, right? So the customer is the user. So with with the optimal performance, the fastest performance you like, and the maximal storage, these are the factors in mind to design a chip, right? But I'm sure, like in future, in the coming future, there's also this important factor, which is environmental degradation. So same is true with, as Professor Jagdish mentioned, when people think of using nanoparticles in human contact, whether it's cosmetics or in drug delivery, wherever it is coming into contact with humans. So there is also a lot of research going on before implementing a new material for a particular application. How good is the degradation capability? So you would like it to be stable as long as you want, but you would also like it to be degradable, So I think in past we have learned our lessons. So that now there is more interest into researching the degradation aspect of all the materials. So I think it's not a straightforward answer. I wouldn't say that we have a straightforward answer to replace all the materials of a chip currently, but this is something into consideration, and that's a very good question. So hope I also answered Kalanidhi Maran about this. So, and over to Jagdish.
Okay, thank you very much, Radha. So as Professor Radha Boya has mentioned, that it's a challenge, and is challenge as a community. But in fact, now there are a group of scientists are working on how to extract useful metals from these electronic waste, so that these valuable metals are been not wasted and also not creating pollution. For example, I've got a professor called Veena Sahajwala at University of New South Wales in Sydney. Our entire center is focusing on how to really treat this electronic waste and then be able to extract out the useful materials, and so that you're able to minimize any of the contamination which you're really creating in these things. So that's why we're educating in Chiang Mai. Before you start doing anything in nanotechnology, start thinking about life cycle issues. Whatever you're starting and what will happen after your usage of 20 years or 15 years or 30 years, and then make sure that after effects are not really having a huge impact later on. For example, in the 50s and 60s, we used to use asbestos as the roofing and all these things for houses, for example. But now we got the realization asbestos is really terrible for human health, for example. So we really don't want to get any surprises in 30, 40 years time. So that's why it is important to initially safety by design. So that's what we have been proposing, and hopefully people will take this one up, sort of thing. But it's a real challenge, Particularly also we are throwing lots of electronic goods, every 2 years, you want to change your phone, and then you're throwing all this electronic stuff. And in fact, that's why Europe, for example, people have developed some cadmium telluride solar cells, for example. European Union said, we are not allowing you to go and sell these things because cadmium is toxic. So, but what the company has done is, and we will sell the solar cells, and after 30 years, we'll take the solar cells back, and we do the recycling and extract all the things, so that you're not having an impact on sort of things. So the new business models are also people are developing, thereby companies are taking more responsible attitude. But government regulation really is important to make sure that the companies don't dump a lot of stuff into the environment and create a lot of problems for the future generations. Very good question.
Thank you, Professor Jagdish. Thank you, Chinmay. Our next question comes from Sonam C. Is she here? Sonam C, are you here?
Yes, sir.
Sonam C, go ahead. Yes.
Thank you so much, sir. While I was researching and being from a computer science background, so this question came to my mind that is there any end to the nano technology? And if yes, so we read about artificial intelligence in computer science. So can artificial intelligence be a different aspect to bring out the nanotechnology to an end? So this is my question.
Okay, Radha, you want to take it or you want me to take it? And please go ahead.
You can take it. You can take it.
Okay, thank you. Yes, the artificial intelligence is not going to end nanotechnology, but what essentially we are doing is that, we are really using something called a deep neural networks, where you're feeding a lot of information to this, essentially systems. And then what happens is that they're learning a lot of information so that they're able to extract out the useful information, for example. By using artificial intelligence, and if you look at images of the x-rays of various patients, for example, and sometimes, the surgeons may miss or doctors may miss some of the features, and then these algorithms are able to pick up some things which missed by the doctors. So that means it only helps us to be able to enhance the diagnosis, for example. In fact, we are using artificial intelligence techniques in our neuroscience project, really try to understand how the signaling behavior is different in the Alzheimer's patients with respect to healthy people, so that you can develop some algorithms and start stimulating Alzheimer's people, their brains, so thereby can hopefully get some functions back and other things. Artificial intelligence is going to play an important role in terms of materials design, for example. And instead of really making material and studying what properties you got, and then you identify what properties I want, and then hopefully we'll be able to develop the artificial intelligence techniques and also enough density functional theory and other techniques. So then it will be able to spit out, this should be the, the arrangement of the atoms, or these combination of materials will give you these properties and other things. So it will be really an exciting development of using artificial intelligence in a broad range of technologies and broad range of sciences. It's an exciting development.
Yeah, if I may add to it, so while we focus, there is these are two independent branches. However, there is an interlink. So there is so much development on the software side, and coding and mathematical formulations of these codings. So there are new softwares and new technology, but this technology will be only enabled by the hardware, which is again built by lots of new materials. So you need new materials which have exotic properties, which can deliver, just like Professor Jagdish mentioned. So you want certain property, you may not be able to achieve it with existing materials in existing dimensions. So you need always these two things go hand in hand to achieve the certain level of desired materials are very, very important. So that's an excellent question, Sonamsi.
Thank you. Thank you, Sonamsi, for asking the question. Next question is Subhadeep Panda. Subhadeep?
Yes, sir.
Yeah, please go ahead.
Sir.
Yeah. Hello, Subhadeep.
Hello.
Are you there?
Yes. Yes, sir.
Yeah, please go ahead.
Good afternoon, sir. I have one question. What is the application of nanoscience and nanotechnology in the neurology? And basically, can I use any nano device in our brain to store our memory data?
Okay, good question. So maybe I'll take this one, Radha. Is it okay?
Yes, sure. It's your area of research. Excellent.
No, thank you. Yeah. So what we're doing, in fact, nanotechnology is really showing a lot of exciting developments in neuroscience. If you would have asked me 20 years back, I can do these things, I would have said, forget about it, sort of thing. So what people are doing with these things, these nanowires, which I was mentioning to you, people are making them as a nano electrodes and then be able to measure the neuronal signals in the brain, for example. In fact, 2 years back, I was at University of California, San Diego. I was working with my colleagues there. And these nano electrodes have been used by neurosurgeons in the Massachusetts General Hospital in Boston. Thereby, they're able to identify which parts of the brain is not really giving any signals for people with epilepsy, for example. Instead of assuming that this part of the brain is the one which is going to really, is the one where you end up having these epilepsy problems, now they're able to actively measure the signals and are able to do the surgery only in the regions where you've got this problem, for example. So really, there's lots of developments. And also nowadays, what we're doing is we're taking the stem cells of the people and then be able to create mini brains and then try to understand how the signaling behavior takes place, for example, with Alzheimer's patients and other things. Again, in this technique, we're using stem cell biologists, neurobiologists, nanotechnologists, and computer scientists with the deep neural networks, artificial intelligence techniques, and working together. Science is really becoming very multidisciplinary, and then this really try to understand each other's language and then be able to really develop these technologies is an important one. There's a lot of potential out there.
Yeah, if I may add to the already wonderful points Professor Jagdish mentioned. So you asked also about storing memory with the nanomaterial. So there have been lots of research on using nanomaterials as memory devices, mimicking how neurons store information by synapses, by electrical signals. There is a communication between neurons by ion transport between which leads to electrical signals. So understanding how neurons work, so people have tried to mimic very primitively. So I would say always the human evolution, and this is the most sophisticated system, whereas the artificial systems that we try to build are nowhere near the sophistication of what already exists in humans. So especially the brain. So there have been lots of research which are trying to mimic the way the neurons communicate. So these are memory. These have memory effects, right? So suppose you have gone through certain. Suppose you have seen something. Even after years, you will remember. You have that memory. So this memory is etched into the neurons. So you have this signaling, which again reminds you that this has happened already. This event has happened. So like this, so the people are trying to mimic using artificial systems. Suppose a company called HP Electronics. They made this memristor, titanium oxide based memristor, and there have been lots of other developments as well, wherein people try to mimic such memory behavior. So you have gone through an event. So next time the system sees that event, it should remember that it has already happened in the past. So there is a difference in electrical signaling. So this comes down to the electrical signaling. So there have been materials which show this property. So not exactly like brain, how much the volume of the data the brain can store. We don't have that capacity, but at least the memory aspect is being trying to mimic.
So they call this as a neuromorphic computing, essentially trying to really mimic how the brain works. Can I really create an artificial neuronal devices sort of thing, if you want to call it that way? Yeah. And of course, finally, to answer your question, can I really transfer my memory into my, another, for example, your computer chip? Probably not yet, but you never know in the future what's going to happen.
I just want to add one thing here. Recently, Elon Musk demonstrated studying a pig brain. So he implanted some device and then started seeing if the pig shows a different temperature. He said he could depict the exact rise in temperature from the neural network. It doesn't need to measure from the pig, but from the network he can study. So lots of further promises. It's exciting, especially in the neural study.
Thank you.
Elon Musk certainly is putting a lot of money into that area.
Yeah, thank you, Shubhadeep. Next question comes from Kevin Abraham. He is from St. Xavier College, Mumbai. Kevin, please unmute. Yes.
Yes, sir.
Go ahead.
Hi. So I don't remember exactly the question, but so one of the questions were so when we as mechanisms get smaller, the relative amount of interfacial area becomes much larger, and so the surface forces become stronger. So as we attempt to shrink to micro mechanical systems, so with the combination of friction and irreversible sticking, so it causes many devices to fail. So how are we avoiding this and bypassing this? Because this will be like clearly a very big problem when it comes to MNTs and other such nano devices. So like using molecular dynamic simulations or like driven nanomechanical systems. So how is this done exactly?
Radha, you want to take it?
Yes. So yes, indeed. So nanomechanical systems have indeed very high forces, as you just mentioned. You know, the forces are much stronger at nanoscale. So you have to so the frequencies at which these nanomechanical systems are also can operate are also higher. So, you can operate with much higher frequencies, and also you have to design coatings which enable these de-sticking behavior. So because particularly this class of system for the benefit of all, so for the class of systems that Kevin is talking about is a nanomechanical system wherein you have oscillating parts within a device. So these oscillating parts are there are movable parts. So what he's trying to say is basically you have friction and surface forces which are huge. So these parts can stick to each other and never come apart. But the advantage with nanomechanics and micromechanics is in more so with nanomechanics is the frequencies that you can operate are much higher, and you have to obviously design materials coatings which can enable these de-sticking. And the friction forces are quite different, especially when you have graphene. So there are many fluids and there are many fluids which display frictionless behavior. So in fact, in the tunnels that I spoke about, so when we studied water flows through these tunnels, so simple water flows, right? So we could see that the water velocity can go up to 1 meters per second. So it's a very huge velocity, and it's possible because it's a friction-free motion. So there is to understand this, you can understand it like this: the water molecules try to stick to themselves rather than stick to the surface. So you can expect new dimensions, bringing new properties. So this completely frictionless nature was possible because of the water molecules sticking to themselves. They do not spread as much on the graphene. So likewise, the condensation is going to differ. When you have two materials which are very close to each other, as in nanomechanics, you have also the ambient moisture can condense. That can also lead to huge forces. So there are detrimental effects which have to be avoided as well. So there are suppose something condenses in between two moving parts, it can lead to just huge forces and just collapses them into each other. So this is also again nanoscale problems which people observe when they make such devices. But it has to be carefully engineered with the right surface coatings. So Jagdish, you want to add anything to it?
No, I think that's good. So essentially, you need to have anti-stiction coatings which will minimize the stiction problem. That's what people have been getting around this particular issue. But also, MEMS devices nowadays could be used for example, injecting drugs for you. For example, people with Parkinson's and other things. People really have got a device which is embedded in the body, and then essentially it's regularly sending the measuring the signals, and then also releasing the drug whenever they need to have, and things like that sort of thing. So really, MEMS devices are finding an enormous amount of applications.
Yeah, indeed.
Thank you, Jagdish, and thank you, Radha. Thank you, Kevin Abraham, for the question. Next one is Isha Malu. She is a senior BSc student. Isha, are you available?
Yes.
Yeah, please ask. Yes.
So, being from a biology background, I was very interested in DNA robots, the nanobots that they have experimented with. And although it's a brilliant idea to cure cancer, there are a lot of problems associated with it. And one of them would be they could eventually self-replicate. And how do you manage the self-replication problem? What if they self-replicate too much, and what are the repercussions it could have? Because there's a whole concept, I don't know if it's fiction or reality, the concept of gray goo. So this postulates that nanotechnology and nanomaterials could acquire the ability to self-replicate and take over the world. I think that's a stretch, but with DNA bots, this is a very real possibility, especially in the human body. So I would like to know how to evade that problem and whether it's a reality or fiction.
Okay, Radha, you want to take or you want me to take?
You can take it.
Okay.
You can take
it. Thanks, Radha. And thank you, Isha. And very interesting question, important question. But in fact, this self-replicating robots is the one which is really gray goo and all these things. In fact, created an enormous amount of scare in the community about nanotechnology. But it turns out that self-replication itself is much more challenging. And what you could do is that you could be able to really make these nanorobots using essentially using atomic engineering, for example. So they can go and do a particular task for you. For example, if you, in fact, one of my colleagues at University of New South Wales, they've created these nano capsules with the camera, for example, in it, and they're able to be sent through the system and able to really get the full picture of the gut, for example. And then you're able to really get a lot of information, chemical information, and all sorts of things, sort of thing. I don't think you have to worry too much about these self-replicating robots and the body and all these things. And the only thing you can do is that you can really send some of these, nanoscale, if you want to call it as a small machines or robots, which can be able to measure the information which is difficult to measure using external techniques. And that's where they can be useful from that point of view. And again, as I mentioned earlier, whenever you're sending anything to the body, we need to make sure ultimately where they end up being. You may ask them to do something, but afterwards, if they're really staying there and particularly getting stuck somewhere in the body or otherwise accumulating in the liver or kidneys and other things, that's not a good situation to be in. And that's where most of the studies are showing that though they do these things and they've got a certain lifetime, again, you use the biocompatible materials, you know that in the biological system you've got, after some time, they dissolve because of the fact that you got a lot of acidic medium in the body and all these sorts of the gut and all these things. So then it's not, that's what people are exploring and making sure that they don't really create any detrimental effects or so.
Yes, if I may add to it, so replication is a very, very, very complex and difficult phenomena. Even so now the biological studies have achieved the sophistication of gene editing. So we can edit genes. One can also induce a replication of cells, but it is still very difficult to do. It's not an easy feat to achieve. Even a growing human outside is not an easy thing. There are a lot of failures even in vitro fertilization. So coming to replication of artificial systems is even more complex. The natural systems come with all the ingredients ready for replication. Still, it is very difficult to achieve. So with artificial systems, with lifeless systems, it's at this moment, I think there's not much to fear about.
Okay, thank you. There is one general question, Jagdish. My father is a farmer. How nanotechnology will help him?
Well, thank you. And your father and I have got something common. And maybe if I tell farmer, my sister always tries to correct me and saying that, oh no, you're a farmer's son, you're not a farmer, sort of thing, So anyway, but I also come from a very small village in a remote part of Andhra Pradesh and Telangana now. So anyway, but coming back to the farming and nanotechnology, there are many things one can do. For example, people are coming with the nano fertilizers. They could be dissolved in water much more efficiently, for example. But also people are developing a wide range of nanosensors which can measure the temperature of the soil, moisture of the soil, and then nutrients in the soil. And then thereby you only go and water the plants whenever you need to water them. You only introduce the nutrients like fertilizers whenever you need to introduce them. So the nanotechnology is going to play a very important role in terms of looking at the crop health and also soil health, and then be able to only do things when it is needed rather than blindly putting more and more water. That means water is a really precious resource. Fertilizers are also, you don't want to really bombard the entire soil with fertilizers, and then the process, what happens, the soil also gets degraded and acidity and other things starts coming into picture. So that's why nanotechnology is going to play an important role. Already people are doing that one. And also robotic sensors and other things are also based on nanotechnology, but also been used for a wide variety of applications in agriculture as well.
Thank you, Professor Jagdish.
Indeed, if I may add one more point. So one is the very important aspect of monitoring, which Professor Jagdish mentioned. So I saw some research in Kaust, Saudi Arabia. So they have a severe drought and usually there's not much water, right? It's a desert. So one of the researchers, Himanshu Mishra, so he was working on conserving water. So they have these nano coatings, so nano wax coatings of sand, so that they can prevent the perspiration of water. So even though there's only little water available, so that should be enough for the farming. So this is on the real field, in the trials on the real field. So they could conserve water much better by these coatings. So with the nano wax, it can coat very uniformly on the sand each of the grains of sand are really coated well, and this can prevent the perspiration and evaporation of water. So this is probably another area, and there is many more, I'm sure, many more areas of research which I may not be even aware of. So
Thank you, Radha. There is one more general and fundamental question. When I read about, when I read about nanotechnology, all the time I hear quantum confinement. Can you brief me what is quantum confinement exactly? What are you confining?
Okay. So Radha, you want to take this one? Or you want me to take it? Or
you go ahead.
okay. So what is quantum confinement? So basically what it is that, say, let me put it this way. If you put water into a plastic bag, right? So then what will happen if I start squeezing it? Then what happens is that the water is rising because instead of sitting at the bottom of the bag, because you're really creating some sort of a pressure on the bag, and in the process it's doing that one sort of thing. Essentially what you're doing is that when you go to the nanoscale, the kinetic energy of the electrons is much higher. So that means electrons are not really sitting at the bottom of the so-called, we call it as a potential well. And then that's what really leads to these electrons sitting at, because of this quantum confinement, at a different energy than normally if you see this one in the bulk material. So that's what we sort of call it as a quantum confinement. For example, if you got a material which is a nanoscale in dimensions, and of course surrounding medium, whether it is air or vacuum or whatever you've got, so that's where essentially the electron energy levels are confined within that region. So that means these energy levels are really discretized, and then they end up having different energies. And say, for example, I cannot force the electrons to go and sit at the bottom of this band called conduction band and a valence band sort of thing. And because of the fact that this additional kinetic energy been really given to the acquired with the electron, it's always sitting at these quantized electron energy levels. So that's what we call it as a quantum confinement, for example. Maybe Radha, you may have a simpler
Yeah,
explanation.
that's a beautiful explanation. That's a wonderful explanation. So, which is very easy to visualize with the squeezing of water. So, you're squeezing electrons when you make these materials too small, and in doing so, you're actually varying you're changing the electronic levels, the orbitals which are making up these electronic levels. So, of these materials. So, basically, you are going to change this electronic structure completely. And this is where the Professor Jagdish mentioned conduction band and valence band. So you are making these energy levels go further apart. So there is a difference in the energy levels of the bulk material to the nanomaterial. So the energy levels can become further apart, and this is why the conduction properties or optical properties are all very different from the bulk.
Thank you. That's a beautiful explanation. I hope students now understood, because although there were 300 questions, many of them are actually repetitive, like same question will be asked in different ways. So this is a general answer for most of you actually. So next one comes like Iron Kezia Leos. She's from Lady Doc College, Madurai. Iron?
Yes, sir.
Yeah, please go ahead.
So I am basically from zoology. I'm doing my undergraduate course in zoology. So I wanted to ask you a question, like whether nano whiskers can they be used in or masks actually can they be used as a personal protective equipment?
I think you're breaking up a bit, Irene. Can you please repeat that question again, please?
Sir, can you hear me now?
Yes, better. Yeah.
Okay, so what I was trying to ask you is, can nano whiskers be used in our masks as a personal protective equipment?
Okay. Radha, you want to take this one, or you want me to take it?
Yeah, so I can start, and you can also add to it.
Yeah, so you go ahead. Why don't you take it?
Yeah. So nano, you specifically asked about whiskers, which I didn't get, but I would generally say nanoparticles. So activated charcoal, for instance, is a very good adsorbent. So even there are commercially available masks which have like layers of particles. So and the commercial N95 masks, they have these layered coatings inside which have porous. So these are like porous polymers and porous materials which can filter out. So there are layers of woven fabric which essentially lead to small pores filtering out bacteria and other filtering out viruses, for instance. So any particles would not lead to your nose. So there are membranes, fabrics, particles which are being incorporated into masks. In fact, we also have graphene mask, so which was distributed to every one of us in the university. So this, so obviously we don't want, because we don't know how safe it is, we don't want graphene to be directly in touch with us. So this is a layer which is in between two fabrics, and that is a filtration layer. So that's what just is the role of filtration. So it is being used. It's a reality. So there have been many commercial products, including the graphene one just I mentioned. And there's also one more question to me in the chat, which was also quite related to this. In nanotechnology effective in COVID-19 therapy? So therapy, I think so far, no. So it's quite dangerous to use anything without much trials and errors, right? So, but there have been lots of this filtration masks, and even there's nanotechnology in many sensors. So you can monitor ECG, and there's like on the skin you can have patched sensors. These all are possible. But so this is where nanotechnology manifests itself into therapies and these medicines and masks. So maybe Jagdish, you can add to it. Do you have anything?
Yeah, sure. Thank you, Radha. And that you've already answered that question. So basically, you can embed these nano whiskers, which you're talking about, in polymer matrices like a composite material. So thereby, you'll be able to really create the porosity such that it doesn't allow any of these bacteria or dust molecules or otherwise viruses to get through, but still air molecules can get through, for example, in this putting these sorts of masks sort of thing. So that's how you can make use of some of these nano whiskers type materials. And of course, has been mentioned, in fact, the Professor Kulkarni, who is a PhD supervisor of Professor Radha Boya, and his team has developed in Bangalore a sort of electrostatic materials, thereby really don't allow these COVID viruses to really pass through these masks or so sort of things. Really very innovative technology they developed as well. So many opportunities for us to be able to explore a wide variety of nanomaterials for mask materials.
So indeed, thank you for mentioning the Made in India technology. That's something I missed to mention. So there you're manifesting the electrostatic nature, as Professor Jagdish just mentioned. So you are repelling you're repelling virus and bacteria by the electrostatic nature. So this is another yet very good demonstration of nanotechnology use in mask technology, which was the current immediate need.
So there was also a question in the chat box, and then the question was, can we use nano robots to know about galaxy and space? And so at this stage, people have been really creating something called nano satellites. And then, of course, these nano satellites need not necessarily be nano, but they're smaller than the standard satellites, and they may be using some of the nanotechnology in order to be able to do this one. And I know that, for example, NASA has made use of carbon nanotubes as sensors for sensing the chemical molecules. And in fact, they have sent it to the rover Mars project. And then, in fact, one of my colleagues, Dr. Maya Mayappan, was heavily involved in this particular project, for example. And then another question was the nanomaterials in satellite solar power. Yes, 3-5 semiconductors, the materials which I work on, people are using multiple junctions of different materials. And by putting these ones, and you're able to absorb the different parts of the solar spectrum, already we can create efficiencies as high as 47% efficiency solar cells. But only downside of this one is they're expensive. So of course, for satellite applications, the cost of satellite is so high, people want to use most efficient solar cells. So in that process, the satellite will be there for a much longer period. So that's why these sorts of solar cells are used for that particular application. But now, since the efficiency has exceeded more than 40%, people are also start thinking about using them for terrestrial applications, using solar concentrator systems, and really focus the sunlight using some parabolic mirrors into 500 suns or 1,000 suns. If you're creating these parabolic mirrors and other things, they're really expensive, then people want to make use of the most efficient solar cells. And again, these multi-junction solar cells have been used.
Yeah, thank you.
Yeah, I have a general question for maybe students also interested. Even myself, I'm interested. Well, when it comes to science, let's say I'm excited by some one experiment that can be Nobel Prize discovery, or I found something which is explained only by the science. It can be high school student or a teacher or whoever it may be. How to keep up the scientific passion that one initiated, or let's say I have generated some scientific passion today, and I want to remain in the science, but that's not possible if I don't retain it, if I don't pursue it further. So at this age, I mean, because almost all are young scientists, so if they're interested but they don't know how to keep it up and how to pursue it further. So maybe I have a question both to Professor Jagadish and Professor Radha Boya. So if you can explain your scientific passion and how are you retaining it, so it's good for everybody.
Okay, Radha, you want to take it? And
you go first. You go first.
Radha is smarter than me, so that's why I'm asking to really respond, and then I can follow her sort of thing.
You're very
You go
kind.
ahead, and
Okay.
please go ahead. Yeah.
So retaining the passion and enthusiasm, that's really an important front, which we all need to work on. Especially we can invigorate some enthusiasm in events like this. So, but retaining the passion is very difficult. So this is where I think to sustain the enthusiasm. So for instance, it could be in my own case, if I have to take my own example. So in my own case, it was I was not thinking that I will become a scientist. So in fact, in many times after the award ceremony, so here in UK, so when they asked me like, what were you thinking of becoming, So and this is again another difference that I see. So many times in UK, at least, where I come across that people have this dream of like becoming a scientist right from the age of 5. I didn't have a dream of even becoming a scientist until the age of until I finished my master's. Until then, I was thinking I should become a civil servant and become a I was preparing seriously for civils, so I never even bothered to take any exams of PhD. So this is where it just changed my life when I went to take this opportunity of internship. So I was selected for the summer research fellowship, and I went and exposed myself to the science, how science is done in real labs, and that changed my perspective. So I completely changed myself from civil services, and I never wrote the exam of civil services afterwards. In fact, I prepared for civil services for quite long, but I just completely changed my dream towards science, because that's what I enjoyed myself doing. So when I was doing this research for 2 months in a lab, so I understood how the research works. So you ask a question, you design a series of experiments, and you try to prove or disprove it by your series of experiments. This is what motivated me. And I advise this to all the young students. So to keep your enthusiasm, look out for opportunities. So for instance, Professor Murthy mentioned, you could go and you could approach. So you could approach scientists. You could make use of a lot of these programs which are offering fellowships at even younger age, like project-oriented chemical education, POSE, POPE. These are the programs from JNCSR. Summer research fellowships from Indian Academy of Sciences. JNCSR also gives summer research fellowships. I'm sure there are many even other opportunities which I fail to list here, but there are many opportunities where you can expose yourself to research in life. So being a part of the research. So I think that helps to keep the enthusiasm. If I had not done the summer research, I would not have taken science as my career. So that's my probably advice. So maybe Professor Jagdish can add to it.
Okay, good. Thank you very much, Radha. And I think it's a very good advice. And so basically, every child is a born scientist. Okay, because when you're a child, you ask question why, how, and why. But then either parents say that, oh no, keep quiet sort of thing, or otherwise you go to school, oh, you're asking too many questions, keep quiet sort of thing. So sometimes I joke about it. Maybe sometimes school can dumb down people and then kill the curiosity of the children. And really, when they are really, kids are really born scientists sort of thing. Okay. So then how do you really keep your curiosity, these things, of course, that curiosity to learn, curiosity to really how the natural world works is the way we really need to be able to encourage children to really think about these things sort of thing. So that's why if you got kids, I would tell you, please don't say that, don't ask questions sort of thing, encourage them to ask questions. And of course, if you cannot answer any question, you can always say that, go and ask your mom knows better than me sort of thing, So that way, at least, both of you will be able to manage the questions and then hopefully be able to answer and then retain that curiosity sort of thing. But how do you really be able to keep the curiosity? In fact, I call myself I never call myself as a scientist. I call myself as a student. And that the minute you start thinking you're a student, I'm always getting into new areas and I'm always learning. I don't know anything about neuroscience, but getting into neuroscience project, I'm learning a lot from my colleagues, for example. So I always tell people that, Vinny Gautam is teaching me more about neuroscience than what I know, sort of thing, for example. Okay. So that's why, when you talk to students also, don't really try to behave like you know everything. I always tell my students, we are learning together. If I have all the answers, we should not be doing that particular project we are working on. I may have more experience of how to really getting around, try to solve the problems, but I don't have all the answers. I can steer you in the right direction, sort of thing. Once if you really start thinking that you're a student, and then you also work with your students as equals, then certainly you learn a lot. Once if you're learning it, that enthusiasm continue to stay with you. And then I think that's why I call myself as a lifelong student. So that's why when I go to conferences, I really don't talk to big professors. I go and interact with students, because that's a fun. Because inspiring students is important for me, but also that they're asking questions, and also it's an inspiring for me as well. And also in the process, it makes me to think as well.
Excellent, Professor.
That's the best.
Thank you. Now I request Dr. Shinji Yamada to share his small presentation because we have given his time for 5. So after that, we will continue a few questions. Dr. Shinji Yamada, can you please share your screen?
Can you see my slide?
Yes, we are able to see, sir.
Okay. Is the screen okay?
Is okay. If you can make it a full screen, can you make it full screen?
Well, I think this is full screen. No.
Oh, is it? Okay, fine. Okay, then fine. Go ahead, sir.
Yeah. Okay. Thank you. First of all, I'd like to thank the organizers for giving me this opportunity to participate in this wonderful event. I'm Shinji Yamada, a senior principal research scientist working for Kao Corporation Japan. Today, I'd like to talk about friction. Friction is a force that resists relative motion between two surfaces sliding across each other. And I have been studying friction and lubrication of various surfaces and materials for almost 25 years. Friction is a very common phenomenon we encounter in our daily life. Friction is, in most cases, a macroscopic phenomenon. However, the origin of friction is sometimes nanoscopic phenomena. And in order to control or design friction properties of surfaces, we have to understand the friction at the nanoscale. Today, I'd like to talk about how fundamental nanoscale research on friction contributes to developing technology and products. Let me start by briefly talking about my company and our products, because most of you may not recognize our company. Kao's business field is very wide, but one of the main fields is the manufacture and sales of daily chemical materials, daily chemical products such as personal care products, just a moment. Personal care products, cosmetics, detergents, and healthcare products. These products are applied on some surfaces and being slid or rubbed when they are in use. Therefore, controlling friction and lubrication properties is quite important for their performances. So, in order to control or design desirable friction properties, we have been conducting fundamental friction research. This slide shows a traditional textbook theory of friction, well known as Monton-Coulomb friction law, which is established more than 200 or 300 years ago, and still recognized as the main fundamental rule to describe general friction behaviors. This theory consists of 3 basic rules. First, friction force is proportional to the applied load. The proportional constant is the most common quantitative parameter of friction, the friction coefficient. Second, friction force is independent of the contact area. And third, friction force is independent of the sliding velocity. This friction theory is established empirically based on the observation of severe sliding systems such as heavy machineries. However, this traditional friction theory does not cover many different sliding systems. In old days, the main goal or motivation to control friction is, for example, easy transport of heavy objects or easy processing of materials. If the friction control is not good enough, sometimes spark like this may be produced. Or control of friction is very important to prolong lifetimes of materials by reducing wear. However, most of our friction systems are not slid under such severe conditions. Applied load is not so heavy and sliding velocity is not so fast. And in most cases, no obvious frictional field may be observed. In these frictional systems, we often find that traditional textbook theory of friction doesn't hold. And so we need a new theory to understand the friction behavior of such systems. This is why we have been conducting fundamental research of friction for many years. One of the most important points to be considered is the contact condition. Let's consider a macroscopic friction system lubricated with liquid lubricant. The contact surface seemed to be smooth. However, at high magnification, visibly smooth surfaces are already actually rough, and the contact between surfaces occurs at the protruding asperities. And we have long believed that the two surfaces, top of the asperities, are in direct solid-solid contact. However, this is not always true. Recent progress of nanoscale experimental technique has revealed that the two contacting surfaces, asperities, are in most cases separated by very, very thin nanometer thick lubricant liquids. This is the state-of-the-art friction measurement technique, the surface forces apparatus. We can measure friction force and viscosity of liquid lubricant with a thickness of few molecular layers. We found that when the thickness of the lubricant film is the order of a few molecular layers, viscosity is increased by more than 6 orders of magnitude than bulk value. This means that lubricant molecules are too thin. The gap between two solid walls is too thin for the molecules to be free to flow like bulk liquids. That's what, namely, the liquids between surfaces not behave like a liquid, but behave like almost solids. That's why lubricant liquids is not squeezed out and remain in the gap. Lubricant liquid properties and resulting friction behaviors at the nanometer scale are very different from the bulk liquids properties and sometimes difficult to imagine. But the lubricant molecules are still remain in the gap at the contact interface. This means that we can control a design friction properties by choosing suitable chemical between them, such as oils, surfactants, polymers, and many different materials can be applied to control the friction. This is the reason that we have been studying molecular scale friction behaviors of various chemicals to be used for our products. Finally, I will show you a recent research on hair shampoo lubrication because this is a very good example of bridging nanofriction analysis and macroscopic product performance. People with long hair often have hair troubles related to tangling during shampooing, particularly rinsing shampoo. Therefore, reducing friction between hair fibers have been a very long-standing problem. Because the contact interface between hair fibers is rough at molecular scale, so we conducted a single asperity contact friction measurement of surface lubricated with variety of lubricant liquids using the friction measuring technique. Parts of the results is shown here. We found that very, very low friction materials that is suitable for this purpose. As you can see, the lubricant C dissolved in water has an excellent friction reduction ability between single asperity contact. Maybe you may know that friction of joints or eye corneal surfaces are the representative example of extremely low friction system. However, this lubricant film, the friction coefficient of 10 to the power of -5 exhibit extremely low friction, much lower than such the low friction biological sliding systems. When we treat this lubricant C to hair surface, we obtain excellent detangling performance. I will show you the movie. These hair bundles are made by heavily damaged hair, and we cannot comb as is shown. But when we immerse these hair tress into a water or a lubricant C solution, then remove from the solution, then comb, try to comb again. Then lubricant C has the excellent lubrication properties clearly seen in this video. And this lubricant C is actually used for our shampoo formulation and very well accepted in the market. Friction is a macroscopic phenomenon. However, friction at the actual contact is a nanoscale phenomenon. So understanding friction behavior at the nanoscale gives us a direction for desirable interfacial properties at the macroscopic scale and suitable product formulations and performance. Thank you for your attention.
Excellent presentation, Professor. Really, I myself felt so happy and exciting to see such a video and presentation, extraordinary presentation. Thank you very much for presenting your work here. If you have any questions, any student can quickly ask one question to Professor Shinji Yamada. Dear students, any one quick question? You can either you can write in the chat box, or you can unmute if possible. Are you able to hear my words, my voice? Yeah, so actually we use a lot of these products actually in our daily use, but we never knew this much science is there behind developing a product. Extremely happy, and thank you for showing such things, Professor Yamada. Yeah, I think we will go to the next question by Priyanka Kumari. Priyanka, are you around?
Yes, sir.
Priyanka, can you go ahead with your interesting question?
Sir, I want to ask, how can we use nanotechnology in algae? As we can know, there are lots of algae. So how can algae be used?
You had one more, no, right? Like, what is the scope of nanotechnology in India and in the world for career? Like, what kind of career you can have in nanotechnology, particularly in India and also in the world? Professor Jagdish.
Yeah, no, thank you very much for that. That's an important question. And then nanotechnology can be being a multidisciplinary field. You can really get into any areas. I would not call it as, for example, if you're biological nanotechnologists, you can go and then start doing work in the areas of targeted drug delivery and wide variety of things. If it is chemistry things, and they can use them for splitting of water and photocatalysis and a range of things. You got a background in physics, and you can go into electronics or photonics and other things. People always ask me this question: where are the nanotechnology industries? I always tell people there will not be any specific nanotechnology industries, and existing industries make use of nanotechnology in their daily products. For example, in the case of computer chips, we're already using nanotechnology. As we talked about earlier, we're using 5 nanometer features or so. So in the same way, in the area of photonics, we're using nanotechnology, and we're using nanotechnology everywhere. So that's why I say that every industry sector will make use of nanotechnology. Depending on your background and your interest, you can go and choose the field which you want to go and work.
Thank you, Professor Jagdish. So the next question is like, can we still reduce the scales? Jivita, are you there? Jivita? Okay, maybe.
And Kiran, there was also two questions in the chat, one to me in person, and also there was a question about how is nanotechnology useful for vaccines of SARS-CoV-2?
Okay.
So this was a question. So I just thought we should talk about it as it's quite current, quite current.
Sure. Please go ahead.
So, so obviously in the vaccine production itself, I don't think any nanoparticles are used, but there's a technology of development of vaccine is quite rapid. This is the first time ever that within a year, span of a year, a vaccine has been developed and is actually given. So usually vaccines development takes decade to do all the process. So the rapid development was in part, especially the new types of vaccines that we have are based on mRNA. So this was possible because again, nanotechnology is quite useful in the initial design of the vaccine. So it was used for, so the lipid nanoparticles were used in the initial phases of mRNA. So the lipid nanoparticles were used for delivering the mRNA and looking at the efficacy of the mRNA. Is it really useful in the initial phases before going to the animals? So that's where it was used in the initial phases of the vaccine design, I would say. So not in the production, but in the vaccine design. So maybe if you have anything else, you can add, Jagdish.
No, I think you answered that question very well, Radha, and then I concur with your thinking. And again, all these new technologies people are developing, whether it's CRISPR technology and gene editing and all these things, is allowing people to be able to precisely design the new viruses and other things. And that's really phenomenal technology, particularly this RNA technology, RNA-based viruses and other things. It's a really very recent development. And I think we will see many more exciting developments of using these things to be able to quickly develop wide variety of vaccines for even things like, for example, people we talk about, why we don't have vaccines for malaria and other things as well. And recently I heard that people have also been developing, some of these vaccines for malaria and other things. For example, in India and other countries, developing countries, malaria is a major issue, for example. So I think it's a sort of a beginning. I think COVID has what it has done. So it has created a lot of problems for the humanity, but also it made people to think in a very smart way and developing innovative technologies which are going to have a much better impact in the future.
There's a direct message actually. I just want to read that. Mari Sailaja typed a question. Are there any specific health or other risk from nano product? If yes, how to overcome or less it? I mean, maybe she wanted to ask if there are any specific health issues due to the nanoparticles or nano products, whether we should remove it or we should overcome it. So that's her question. Maybe your answers can help them.
Okay. Radha, you want to take or you want me to take and you'll follow? Okay, thanks, Radha. Thank you. So basically, of course, it depends on what nanostructures you're using. For example, the nanostructures which are using in a computer chip, and there are no health issues because they're all packaged and other things. But if you got a nanoparticles in a powder form, for example, and of course they may be floating around and you maybe breathe them, they cannot see them and other things. So that's why we always tell people when you're dealing with things like nanoparticles, always use them in the fume hoods and also wear such right kind of mask and other things so that you're not exposing yourself to these nanoparticles or so sort of thing. But once if you embed them into composite materials and other things, it's not a major issue. But then again, when you're really, for example, if you're embedding some nanoparticles in a membrane, if you're bending this or flexing this membrane, are these nanoparticles are going to come out and other things and where they end up being. So those are the things one need to really look at. So that's why we have been educating from the beginning that, always you're designing something, always design, keeping the safety in mind rather than design something and afterwards look at the safety of the issue sort of thing, So that's why it is important to make sure that we do that one. Yes, if you really get exposed to, for example, people have done studies, what is impact of carbon nanotubes? And if you got, large amounts of carbon nanotubes are really clustered together, they act like asbestos and, then you get to have lung problems and all these things as well. So those are things one need to always keep in mind. And again, when you're using them in cosmetics, and then we talked about earlier, and how they end up being and where they end up being. The full life cycle issues need to be kept in mind. And without only thinking in a short term, yes, they are very useful and you will use it. And if you're not thinking about life cycle issues, and we may create problems for the humanity in the longer term. So that's why the caution is always needed.
Indeed, that's very important point Professor Jagdish makes. So basically, if there is any technology where human contact or even human or even animal contact is like anticipated. So not like electronics, but indeed, like if it is a drug delivery or any other form of injection or even in skin contact, I think one needs to be very careful about the evaluation of a material like nano material. So in fact, there's a lot of these buzz about graphene oxide being very useful for drug delivery. So, but there's also in Manchester, we also have a lot of research going on the safety and efficacy, or even beyond efficacy. What is the safe haven? Is it really a safe thing to put graphene into a body? So basically, the studies include like, is it excreted out of the body, or does it end up just being there inside various organs? So I think these are the studies which are very as important as the hype of the nanotechnology itself. And the usefulness of nanotechnology is very much like even the viruses, right? The SARS-CoV-2 virus is also few hundreds, like less than 200 nanometers. So but as long as you use nanotechnology and nanoparticles for the right thing, it's quite useful. So for instance, there were studies as the SARS-CoV-2 spread. How does SARS-CoV-2 spread? Without using the virus, actually using the nanoparticles. So these were simulated. So how the particles, I mean, how those similar sized particles would float, how long they would float, how long they would stay in there. These studies were not done with actual virus itself, and how long this SARS-CoV-2 will stay on the surfaces. These are done with passive viruses. So, but all these places, nanotechnology was tremendously useful, even to understand the spread of the particles. So I think one has to be careful when it is to be used in any human contact or animal contact.
Yeah, thank you, Jagdish and Radha. There are so many questions, Professor Jagdish. Almost, I mean, even I feel very bad actually. Like if we have to conclude a session, I feel very bad because so many students with so much of excitement and enthusiasm, they ask so many questions. Since we cannot answer all, that is why I have chosen few questions related to different fields, and you were able to answer them. One question, very interesting question came, and I think it is also important students should know. What did you achieve in life as a nanoscientist? And Jagdish, what did you achieve in life as a nanoscientist? And why I should choose science career when there are other markets, are very attractive. So I want your answer for this.
Okay, good. Okay, that's good. So then maybe short answer is, what did you achieve in nanotechnology? I can short answer is nothing much. Okay, a serious answer is that the fun of doing science is something really great. I enjoy doing science because I'm enjoying it. People ask me, how can you possibly work for 40 plus years? And, when it's sort of, more or less 7 days a week, as soon as I get up, I'm in front of my computer. Before going to bed, I'm in front of still my computer sort of thing. But I don't see that as work. I'm having fun. If you like video games, if you're playing video games, and if your mom or dad are asking you, come and have a dinner, you want to come later and you want to later, you never look at your watch because you're having fun. So that's what exactly I'm doing in terms of having fun doing science. So what is the biggest thing which I feel as my proud thing? Of course, we do a lot of interesting science, and we develop lots of technologies which are used in, for example, lasers which we developed are now used in internet and all these things. That's not the proud part of it. The proud part of it for me is the students and postdocs whom have gone through my laboratory and whom we have trained and mentored in my laboratory and also globally. Seeing their success is the biggest happiness which I get from. It's not about myself. And my recognitions, my awards, they're all always secondary to me. Seeing young people, inspiring them, and then really motivating them and then steering them in the right direction to achieve their dreams and goals, and seeing their success makes you very happy. So that's why I always tell people, pleasure of giving is much more immense than pleasure of receiving. Once if you start enjoying the pleasure of giving, you never look back. But also you have to pity people, those who never experience the pleasure of giving, they don't know what they're missing out. Okay? So that's why I always tell people who start helping other people, that really gives you an enormous amount of happiness and satisfaction. you'll never look back. That's been the most fun part of my life. What did I do? Helping other people to achieve their dreams and goals. That's the most happiness which I get from it.
Great, great, Professor. Radha?
So beautifully put. There's no other way to put it. So I have only few things to add. So as Professor Jagdish mentioned, so this is one job where you don't feel bad, like, oh, I have to go to the work again. Every day morning you get up and, oh, I have to go to the work again. You don't feel that. So most of the people I know of working in science, there may be a few odds, but most of the people whom I know working in science and nanotechnology, in science in general, so they enjoy doing their job. That's why they're doing science, including myself. So I think that's the most fun part, and working with brilliant people. So you get a chance to work with intelligent, brilliant, smart people around you. So there could be students, there could be mentors, there could be colleagues. So it's all in all, you're surrounded by intelligent, motivated, highly motivated, and smart people. So this is a privilege, I think, to be in science. So,
Thank
and
you.
I wish
Thanks
all
a
the
lot.
best for all the students.
Professor Shinji
Again,
Yamada? Sorry, Jagdish.
No, sorry. Only thing which is, if you're not having fun, get out of science. You have to have fun. Okay?
Excellent, Professor.
Please go ahead.
Professor Shinji Yamada, can you suggest something to the students about science, nanoscience, how interesting it is?
Well, I'm a company researcher, but and we have to make a good project for people. But sometimes we have to do fundamental research which is suitable for understanding the phenomena in the daily life. So industrial research is also quite important and exciting. So maybe young students may have interest to becoming an industrial researcher. Thank you.
Thank you, professors. It was an excellent session. Actually, I like to stay 2 more hours here. Whatever my wife thinks, I don't care now. So I want to conclude this session, but I want to ask students to excuse me, because as you know, we cannot exceed the some more time. So whatever questions you have, either you can mail to the professors or you can contact our experts also in our university nanotechnology department. There is a dedicated department for nanotechnology. There are more than 80 number of faculty members are working on nano related things. So you can write to us, you can write to professors. You please be in contact. And we are now moving to the most awaited event, awards announcement.
So, okay, Kiran, if you don't mind,
yes.
I have already given my email address, and Radha also gave her email address.
Great.
And so feel free to send emails to us, and we'll be happy to answer any questions we could not answer. Sorry that we're running out of time, and
sure.
It's already, by the way, 10 p.m. for me in the night in Australia. So we're ahead of your time. So then, of course, I'm happy to stay. But again, you can always contact us, and we'll be happy to respond to your questions whenever it is possible.
So, Professor Jagdish,
Sure. Indeed. Thanks for making that statement, Jagdish.
Can you please announce the awards, Jagdish? The first 5 maybe you can announce. I'll share the screen. First name.
Yes, sure. Okay, let me get out okay, let me see. Showing something else. Okay, let me see how it's gone to there. Let me close this one. So
to your mail I sent.
Yeah, no, sure. I got that one. So that I'm just checking and see. Okay. It is fantastic to see that I understand that the judges had a very difficult time in terms of choosing only 10 people out of so many wonderful, bright young people, and they were so impressed. But unfortunately, they only had to choose 10. And I would like to say that let me congratulate all of you, those who participated in this competition, and all of your winners. You got the opportunity to really interact and participate in this wonderful program. Okay, let's give a big hand to all the people, those who participated in this program. So they then will go one by one. And so the first name I'm going to, of course, there are 10 winners, and we'll go one by one, awardees. And Mr. Abhinav Kumar. And so from St. Karen's High School, Gola Road, and Danapur, Patna, Bihar.
Yep.
Congratulations, Abhinav Kumar.
Congratulations, Abhinav.
Well done.
Yep.
And the next winner is Miss Preeti from Miranda House, New Delhi. Well, congratulations, Preeti.
Congratulations, Preeti. Well done.
And Miss Chinmay Chahar from Indraprastha College for Women in University of Delhi. Congratulations, Chinmay. Well done.
Congratulations, Chinmay. Taking time, I think. Just a second.
Okay, sure.
Full screen is taking time. Okay. I'll stop and again share it. Sorry.
Okay, sure.
All are like this, or oh, maybe okay. I'll share from my other system then. I'll just stop here. Yep. Chinmay done? Yes.
Good. Well done, Chinmay.
Well done, Chinmay. Next.
Yeah. So the next awardee is Miss Ayushi Das from Miranda House, New Delhi. Congratulations, Ayushi.
Congratulations. Yep.
Yep. Okay. Next winner is Miss. You've done that one, Kiran?
One more is there. Yeah, I'm done.
Okay,
Yes.
sure. No, that's fine. Okay. So then Miss Niveda S from Women's Christian College, Chennai, Tamil Nadu. Congratulations, Niveda.
Yeah. Radha?
Yeah.
So now
The
I'll
next
ask Mr.
awardee-
Radha Boya to go ahead. Yeah.
Sure, Jagdish. So the next awardee is Mr. Kevin Abraham from St. Xavier's College, Mumbai. Congratulations, Kevin.
Yeah.
Great achievement. Our next awardee is Miss C. Irene Kezia Lois from Lady Doak College, Madurai, Tamil Nadu. Congratulations, Irene.
I was confused. I asked her whether your name is Irene or Iron. She said, I am Iron, sir.
So she's a true iron lady.
The true Iron lady. Yeah.
So our next awardee is Miss Ritvika Panda
Great.
from Day Public School, Chandrasekharpur, Odisha.
Yep.
Congratulations, Ritvika. Well done. And our next awardee is Miss Sonamshi, Indraprastha College for Women, University of Delhi.
Great.
Congratulations.
Yep.
Congratulations, Sonamshi. Our last awardee, last but never the least, Mr. M. Kalanidhi Maran, Marg Vidyalaya, Chennai, Tamil Nadu.
Congratulations, Kalanidhi Maran.
Congratulations.
He was a ninth
Hearty
class student, actually. He's a ninth
Yeah.
class student. He did very well.
It's fantastic. You know, he's the youngest winner. You know, well done.
Yes,
Well done. Keep it up, all of you.
Yeah.
Well done, Kalanidhi Maran. And being a woman, if I can add one sentence here, I'm quite happy to see so many girls interacting. It's so lovely to see you all the students. And in fact, I mean, I just love that there are so much age spectrum of the students, starting from very young age to intermediate and above, and even degree college students. But my particular love goes to all the girl students over there. Girls, go ahead and pursue your dreams, and also boys. So I'm not biased, but I'm particularly interested that I'm pleased. I'm pleased to see that girls are doing as well as boys.
Yeah, actually, I want to mention here, along with these merit certificates, students will, merit students will receive 1,000 rupees cash prize also from the Indian Science Congress Association, Chennai chapter, in celebration of Department of Science and Technology, Government of India Golden Jubilee year. And also these students will be allowed now to visit our nanotechnology laboratories, to interact with our faculty members, and they can do a project. Not only these 10 people, whoever is interested in this nanoscience and nanotechnology, they are most welcome, and our doors are always open in SRM University. So with this, I would like to thank all the panel members for their for spending a lot of their valuable time In fact, why I chose Professor Jagdish is I met him when I went to Australian National University as a postdoctoral person. Although I didn't work under him directly, but I became a big fan in few days of time. Why? Because he respects time a lot, and that's why time respects him. Now I see. Yeah. So and also great scientist, great motivator. Even if fifth class student, if he asks a question, means he will answer very actively. And he has a lot of endowment activities, and he is the highest civilian. He is the recipient of highest civilian honor like Bharat Ratna, like our Professor C.N.R. Rao. He received from Australian government for his outstanding contributions. He gets millions of dollars for his projects every year. It was my fortunate. I mean, I'm lucky to be associated with him. Thank you, Professor Jagdish. You immediately accepted. Within 5 minutes, I received a reply. Yes, I will do it. It is important to inspire the students, he said. I'm so glad. And Professor Radha Boya, I knew about you from various sources. You worked in Nobel laureate. That itself, Professor Andrew Gim, great. I knew about you.
It's my pleasure to be here, and
Yeah,
I'm
once
really
we
honored
want
to be
to,
here.
we want to see you in our university very soon for a special talk we will arrange. Professor Shinji Yamada, my colleague, Dr. Yuvraj, actually suggested brilliant, world-renowned scientist and R&D specialist Shinji Yamada. You please invite him. He is the one who can actually make the entire session very active. So his talk, I mean, I'm so impressed because directly we're able to see the product, whatever we are using daily, how much science is involved under behind that. I'm so glad to see that. Thank you so much, all the panelists. John sir, my dean sir, my chairperson sir, I'm very much thankful to you. You are with your support only all this is possible. I hope it went well. I hope you are happy. Thank you so much. Now I hand over the session to Professor Kashmir Raja and then ISCA Secretary Dr. Alagirisamy to say vote of thanks. Sir, unmute, sir. Sir, unmute. Please unmute, sir.
It is not, now it's okay. So, as Dr. Kiran said, now this program is a very fantastic one involving the young students, young budding scientists, and all their queries were properly answered by the panelists, especially Channaputti Jagdish and Radha Boya. And this is a very, very interesting and informative session. I thank these scientists, Radha Boya, Channaputti Jagdish, and also Yamada. And I feel that such sessions should continue in the future also. And I congratulate all the winners. And they are awarded with certificate and also 1,000 rupees. And we are very happy from the Chennai chapter of Indian Science Congress Association in associating with ICON and offering this award to the young students. And I am very happy to say a few words about Dr. John Thiruvadigal. When I approached him, he was very accommodative. And he said there is a separate session, a special session in this icon. You can take it up. I immediately said, yes, sir, we'll do it. And this is his magnanimity in offering such a session to another sponsor. And we are not only the sponsor, we are jointly organizing this. And so I thank John Thiruvadigal. He is a former dean and now he is the chairperson of the Applied Sciences. So I thank him on behalf of the Indian Science Congress officials. And I also thank Dr. Kiran. From the day one, he was contacting me and he is doing all the helps needed to host this event. I thank him also.
Thank you,
and along with Dr. Kiran, there were many professors from Department of Physics and computer, nanotechnology, they also interested in our involvement, and they helped us. So I thank them also. And finally, I thank our treasurer, Alagiri Sami. He is an important person in collecting the reports from our activities in other institutions also. And he used to prepare the final report to be sent to the Indian Science Congress Association. Now he is going to propose a lot of thanks. I thank everyone in the SRM Institute of Science and Technology. Thank you very much. Enjoy. Good evening.
So, thank you, sir. I'm Dr. Alavisami. I'm very happy to propose a vote of thanks. And already Kiran and many members have almost covered a vote of thanks. So, thanking everybody. At the outset, I thank all the participants who joined with us. And I'd like to mention that the Chennai chapter is the second activity as a virtual platform. So many activities we have joined with physics department, and this is the first time we are joining as the virtual conference. So I thank Professor John Thirubadigal for taking each and every moment and spending a lot of time. And I thought that the meeting will end up within 1 hour, but 3 days back, the meeting ended for 4 to 5 hours, and taken each and every moment just like a bird movement. And especially with the focal theme of Chennai chapter that is called Local Indigenous Pathways to Succeed, especially for the young minds. So Chennai chapter is always involving seeding science to the young minds, but this time this is seeding nanoscience to the young minds. So I was thinking about does science involve nano or nano involve science? So I was thinking all the time, I was looking for the internet, and so I was not able to get it answer. So I hope get the answers later. So on behalf of the Indian Science Congress Association Chennai chapter, let me thank ISCA President Vijayalakshmi Saxena for the kind support and willingness to join here this special occasion, and I shall thank them for financial support. Otherwise, this workshop or conference would not be materialized, and we were able to capitalize many activities. So I thank Professor B.S. Murthy for seedings to the young generations, and he was mentioning that we are not the young generation, something we can mention that is called next generation product. For your information, I used to visit his YouTube, Role of Advanced Materials in Transforming India. I don't remember exactly the title of the YouTube lecture series, Role of Advanced Material in Transforming India as a Global Leader. So Indian Science Congress needs such kind of transformations. So, and I thank Professor Senibadi Jagadish for the nice interaction with the school students. And he always, I would like to put the word that a complementary information that he always enable Radha Bhaiya is relatively young. I thought it's relatively young, but the moment I hear so many things, Mesmeri talk, and I got an opportunity to listen to a talk in JNCSR that we are combined together in alumni talk, and she delivered the talk for interface layers and mono layer. I thought that she would cover here, but later on one student he made to cover the Radha Bhaiya's talk. And really I thank all the professors, I thank all the invited guest speakers who have shown their works, and especially I thank Sinji Amada for this mechanical friction, how that is connected with nano, and he set a benchmark for all the things. And I thank all the members who are involved in the spheres to making this event as a grand success. So one thing I just want to mention that ISCA Chennai chapter is always looking for the measurable indicator. Measurable indicator means what the scientists, what the people will transfer the information to the students, and those students will get the knowledge that is called a retentivity. So that retentivity is just like a capacitor measurements, how much knowledge they just store the information, what is the evaluation, and then what is the transformation that will come as the product. So as the indigenous product is an asset. So Chennai chapter and associated with the Chennai chapter always be considered as asset. And I thank you all for the gathering here. And some students, they ask questions, so many questions, but I noted all the questions. But I wonder some questions were not placed here to Radha Bhai. Radha Bhai is very happy to answer. And Chenubudi, Jagadish, is it, what about the top to bottom approach and bottom to top approach? What did you achieve? Instead of asking the question, what did you achieve so far, or what are the compromise that you are being as a nanoscientist? So there are so many questions that is mind-boggling to me. So let me ask them later. So I thank you all for gathering here, and thank you very much. Thank you very much. Thank you.
Thank you all. So we conclude the session now. So I thank everybody, whoever have participated in this. Yeah.
Okay, thanks, Kiran, and then entire SRM team, and then Indian Science Congress Association team for inviting us and then giving us the opportunity to interact with the bright young people. We enjoyed spending time with them. Thank you very much.
Thank you. Thank you.
Thanks so much, entire team SRM, and especially Indian Science Congress for playing a key role in shaping up the next generation scientists. It's very much required. Yeah, at this moment, I think Indian Science Congress and taking a special interest on this is much appreciable. Thank you so much. It's my pleasure to be a part of this.
Thank you.
Bye-bye, colleagues. Bye-bye.
Thank you. Bye.
Pleasure seeing you, Radha. We'll keep in touch. Thank you.
Indeed, my pleasure. My pleasure.
Thank you,
I've heard a
Professor.
lot about you from colleagues and friends.
Thank
even
you.
from yeah, it's my first time meeting you. It's
Anyway, Vinny sends her greetings to you, and then I mentioned to her that I'll be meeting you, sort of thing. She said that you both keep in touch and all. So.
yes, indeed. So I've heard a lot about you, and it's my
you.
honor to meet you. Yeah.
Pleasure meeting you too. I heard a lot about you too, so it's fantastic. What you're doing is fantastic, and keep it up.
Thank you.
Thank you,
Hope
Professor
we meet
Shinji.
sometime offline. Yeah.
Thank you. Sure. Thank you. Bye-bye.
Namaste.